So you can continue. This way.
Okay. Good morning to everybody online and the people that are on ground. The title of today's presentation is on quantum computation. But before we actually discuss quantum computation, we need to avail ourselves of the rudiments of the classical computing, because the quantum computing is based on the classical computing. So meaning that the knowledge of classical computing is very, very important in quantum computing. The use of computers for carrying out calculation is started in the 16th century. And at that particular period, computers occupy large spaces. We can have a computer that can occupy an entire room. But as technology advances, many things came into place. So we now have personal computers on our desktop, and even the smartphones that we all carried along is our computer itself. Because with your smartphone, you can do a lot of things. You can program on your smartphone. You can do a lot of computation on your smartphone. And you can see the size of a smartphone compared to a large computers that has existed in the 16th century. So that shows that technology is advancing at all time. Now it is projected that quantum computers will now occupy the position of classical computers in the nearest future. And that is why researches are still ongoing on the quantum computation. So the basic understanding of classical computers are vital in knowing how it works.
Okay, that's good.
Now, let us start from the basic, that is the fundamental. If we have a coin that is not resting on its edge, the coin has two states. That is, it can bear the head, which is represented by H, and the tail, which is represented by T, as shown in figure 1 below. So the two coins will now have 4 possible states. That is head and head, one coin having head, the other one also having head. That is why we have HH. Then one coin having head and the other one having tail. That is how we have the HT. Then the other one can have the tail and the head. That is TH. And when both coins have tails, we have TT. So it means that for 2 coins, we have 4 possible states indicated by HH, HT, TH, and TT. Now, if you now extend it to 3 coins, we now have 8 possible states. That is HHH, HHT, HTH, HTT, THH, THT, TTH, and lastly TTT. Now, if we have 2 coins, we have 4 possible states. And that indicates that n is equal to 2. Then if we have 3 coins, we have 8 possible states, showing that our n is equal to 3. So n represents the numbers of coins. So generally, if you now have n coins, so it is possible for us to now have 2 raised to power n possible states. Another way of describing information is by using die. And usually a die has 6 sides. So a 6-sided die will have 6 possible states. That is state 1, 2, 3, 4, 5, and 6. If we now have 2 dies, so meaning that our n is 2, then we now have 36 possible states, which is listed below. Then we can now extend it to n dies. So for n dies, we have 6 raised to power n possible states. So you can now see that the information that can be encoded, that is represented by die, is not as much as that of by coins is not as much as that of a die. So meaning that we can use coin or dies to encode information, that is to represent information. Another way of representing information is by using color. The rainbow color, red, orange, yellow, green, blue, indigo, and violet, can also be used to encode information. Now, if we now have the 7 colors of rainbow, and it can be memorized easily by using the acronym ROGBIV. Sometimes some people use Richard of York, Gain Battle in Vain, to memorize the 7 colors of the rainbow. And if we now have 3 coins represented by the possible state and 2 dies, then it is possible to encode information using the 3 coins and the 2 dies. So we now have the possible state for the coins and that of the dies. And the color, starting from red, orange, yellow, green, blue, indigo, violet, can be used to encode information. Now, if we refer to color green, it is not easy for somebody to just say this color is green. It is the information that is obtained from either the coins or the dies that will actually encode what we have in mind. So if you have 3 coins having HTT or 2 dies having the possible state 1 and 4, so that corresponds to color green. So all others possible states are not so relevant. So the ones that are so relevant are the ones stated. So a coin will now carry less information than a die because it has 2 possible states. Physical bits. If we consider a coin having 2 states, that is the head and the tail, we can represent the head and the tail by using the binary number 0 and 1. So 0 can represent the head, so while 1 represents the tail. So the physical system usually has a binary digit being represented by 0 and 1. So the binary digit is now abbreviated as bits. So it means that a bit is the smallest unit of a classical information. So just like I had here in the previous slide, when we have colors and the possible state of coins and that of the die, we have the information that can be used to represent the thing. Now, if we now have 3 coins, so the 3 coins will have its possible state. So we can now replace the 8th possible state by using bit, which is 0 and 1. We can make use of 0 to represent the head, so while 1 represents the tail. So for the 3 coins, instead of stating the head and the tail, we can represent it by 0 and 1. And that 0 and 1 is what is called the bit. So for the first possible state, which is HHH, it will now be 000. Then the second one, which is HHT, will now be 001, up to TTT, which is 111. So these numbers are called binary numbers, or base 2. So in terms of information encode, they can sometimes be called binary strings or bit strings. So it is possible to convert the binary string to the decimal string that we are all familiar with. So if we have the bit represented by 11, 0, 1, 0, which is binary, that is base 2. Then it is also possible to encode in decimal, which is the usual base 10. So we can see that in the conversion, we have 1 times 16, then plus 1 times 8, then up to 0 times 1. So we can see that the leftmost side, which is a 16, it carries a lot of information. So that shows that it is the most significant. So while the rightmost side carries less information, so and that indicates that it is not significant. So the one that is significant carries a lot of information. So the leftmost bit contributes 16 to the number, and it is the most significant bit. So while the rightmost contributes only 1 to the number, and it is the least significant bit. Then there are also, apart from the binary numbers that classical computers uses are hexadecimal. So hexadecimal means base 16. So just like we have for the binary number, which is just 0 and 1, the 16 digits of the hexadecimal base now ranges from 0 to F. So we have 0 to 9, then A to F. So the 10th number there, which is A represents 10. So B represents 11, then C represents 12, D represents 13, E represents 14, then lastly, F represents 15. So just like the conversion of the binary string to the decimal string, it is also possible to have a conversion of the hexadecimal string to the decimal string. So let's look at a typical example. The number represented by F2A is hexadecimal because it contains both alphabets and numbers. So that hexadecimal number, F21, can be converted to decimal, which is base 10. So converting to base 10, F2A, because the base of hexadecimal is 16. So we have 16 raised to power 2, then dot F, then plus 16 raised to power 1 dot 2, then 16 raised to power 0 dot A. So 16 raised to power 2 is 256. And by the time we had everything together, we have 3882. So hexadecimal converted to decimal, that is F2A, is now 3822. So it is possible to convert that decimal to the binary number. Now, one of the code that is used by the classical computer is the HTML. So the HTML uses hexadecimal to code colors. RGB. So RGB stands for the additive primary colors. R standing for red, then G stands for green, then lastly B stands for blue. So it is possible to add the colors together. So the amount of red, green, and blue for the hexadecimal ranges from 0 to 255. So 0 means none of the color. That is none of red, green, and blue. And 255 means the full amount of the color. So for the hexadecimal, it ranges from 00 to FF. So let's look at a typical example of hexadecimal numbers that is used by the HTML color code. So we have FA 10E4. The first FA represents red. Then 10 corresponds to green. Then lastly, E4 corresponds to blue. So if equal amounts of the colors are now added, it will result into bright pink. Then another way of representing information or encoding is what is called ASCII. So ASCII stands for American Standard Code for information interchange. So usually computers encoded letters, numbers, symbol, and some special command using the ASCII code. So the ASCII code uses 7 bits, and just like the coins and die, the 7 bits will now have 2 raised to power 7 possible state, that is 128. And that means that ranges from 0000000 to 111111. And the ASCII code can be used to represent different information. So let us look at a typical example of the ASCII code, which is used to represent information. So we have the table 2. So in that table 2, you have the binary digits, its decimal equivalent, and the special symbol. So using the ASCII code, the first 8 represents T. Then the second 8 represents O. So while the last 8 digits will now represent M. So combining the 3 together will now give us a name, which is a Tom. So usually the classical computers, which is based on the binary string, will now be able to encode the binary string to represent a name. And a modern way of encoding is the UTF. So the UTF stores a lot of information. So unlike the HTML, which uses 7 bits, the Unicode, that is the UTF, Unicode transformation format, it uses a 32 bit. So you can see that it will encode a lot of information. And that is why research is still on to use a different code to represent information. Then logic gate. A logic gate is one that has input and output. So the gate does or perform operation on the input to give the output. So the simplest logic gate takes 1 bit as input and 1 bit as the output, and that is represented by the figure 3. So the input is a single bit, and which can be 0 or 1. So that type of gate that its input is still the same thing as its output is what is called the identity gate or the buffer gate. So for the identity gate, you have the input is still the same thing as the output. So if the input is 0, you expect the output to also be 0. If the input is 1, the output is also 1. So that type of gate is called identity gate or the buffer gate. Then we also have the NOT gate. For the NOT gate, it flips between from 0 to 1 or from 1 to 0. So meaning that the NOT gate will now negate. It is also known as the inverter gate. So if the input is A, as it passes through the triangle, you can see the small circle. So the small circle shows the operation it performs. So because it negates the input, so if you have 0, since it negates it, it will have the output will be 1. And if the input is 1, if it negates it, the output will be 0. So that is not a gate. So it is now possible to combine 2-bit logic gate. So meaning that we now have 2 inputs represented by A and B. So A can be 0, B can be 1. So if we now try to combine the 2 inputs, then we have 2-bit gate. So if the input is A and B, so when it passes through the gate, the AND gate, then it produces AB. So AB is just like the normal multiplication, that is A multiplying B. So let us consider when the input is equal to 0. That is A is equal to 0 and B is equal to 0. Then the output is 0. So when we have 0 and 1, the output is 0. When we have 1 and 0, the output is also 0. So for the AND gate, it can only give 1 as the output if the 2 inputs are 1. So let's look at it in another way. 0 times 0 is 0, isn't it?
Yes.
Then 0 times 1 is also 0. Then 1 times 0 is 0, and 1 times 1 is 1. So the AND gate is analogous to the multiplication. Okay, So the symbol used for the AND gate is shown there. Then we also have the OR gate. So for the OR gate, if the input is 0, then the output is also 0. So every other ones are 1. So for the OR gate, it outputs 1. That is, if either or both is 1. Okay? And otherwise, it is a 0. So that is why if the input A is 0 and B is a 1, so the output will be 1. However, if both are 0, then the output will be 0. So you can have 2 bits, A and B, as they pass through the gate, the OR gate. Then you have the output represented by A plus B. Okay? But if you look at it, it's not the same thing as that of the AND gate, where we have multiplication. If you look at A plus B, you expect that A plus B, that is 1 plus 1, should be 2, or simply 0 and 1. Then we also have what is called the exclusive OR gate. So the exclusive OR gate is represented by XOR. So XOR gate, it outputs 1 when only one input is 1, but not both. So meaning that if you have the 2 inputs as 1, the output is 0. And if you have the 2 inputs as 0, when they are the same, it has a 0 as well. So every other ones are 1. We are trying to look at the fundamental classical computing, so that when we go into quantum computing, we'll have a good background. So the XOR represents the exclusive OR, and the addition is in that of modulus 2. For example, 0. So 0 is still the same thing as 0 mod 2. So 1, the same thing as 1 mod 2. Then 2, that is 0 mod 2. Then 3, that is 1 mod 2. Then up to 5, that is 1 mod 2 as well. Then we have NAND gate. NAND gate means not and, that is, it negates the AND gate. So for the AND gate, which is similar to the multiplication, so you can see the small circle. So the small circle negates the output, and that is why you have AB. Then you can see the long bar. So the long bar shows negation. So for the AB, so if you have 0, 0, then for the NAND gate is 1. If you have 0, 1, for the NAND gate is 1. If you have 1, 0, for the NAND gate is 1. Then if you have 1, 1, for the NAND gate is 0. So it's negating the AND gate. Then we also have the NOR gate. So NOR gate is negating OR gate. That is why it is called NOR gate. And its output, the output for the NOR gate is 1 when you have both input as 0, 0. Then others are 0. So for the truth table as shown there. So for the NOR gate, because it negates OR gate, so you have the inversion symbol, and that is the small circle. Okay, so we have NOR gate. Then it is possible to combine 2 AND gates together. So if you have the first one is A and B, so the output is AB. Then if you now try to combine C with that of the output, you have A, B, C. And that is an example of a multiple gate. Then the logic gate can represent physical circuits. So in the physical circuit, you have the battery, okay? So in the battery, you have the positive side and the negative side. The positive side is represented by the bump, okay? So while the negative side is flat. So for the battery, then you also have two switches. Switch will allow the inflow of current. Then you have a light bulb and a connecting wire. So for the first state, when A is 1, when A is 1, it shows that the switch is on. Then for the second one, when B is 1, the switch is also on. So as the current passes from the first switch, which is on, through the second switch, which is also on, then you can see the output. The output is being represented by the light bulb. So you can see that the light bulb is also on. So that is representation of the logic gate. That is how logic gate can be used to represent a physical system. Let us look at another one. When the first switch is off, when it is off, it is represented by 0. And the second switch is on. When it is on, is represented by 1. You can see vividly that when A, the first switch is off, current will not be able to flow through. And to flow through the circuit. And because the current is not able to flow through the circuit, we have the output as 0. So the light bulb is off and the output is 0. Then another case is when A is switched on. When A is switched on and B is a switch off. So you can see that the output is equal to 0. Then there is another case when both switches are off. When both switches are off, you agree with me that the light bulb will not show. So when the switch is on, it's represented by 1. And when it is off, it is represented by 0. So that forms the logic gate. Okay, so we have the truth table for this circuit, and that represents the AND gate. So for the AND gate, it can be on. The light bulb can be on when both switches are also on. And that is why you have 1, 1. 1 represents that the first switch is on. Then another one represents that second switch is also on. And that is when the light bulb will show. So this is just the rudiment of the quantum gate. So if we now consider another case, when one switch is on, okay? Sorry, when the switch is off. So when the switch is off, you will see that the current will not be able to pass through that switch. However, the current will flow through the connecting wire and passes through the light bulb, and the light bulb will be on. So you can see that even if we have A to be 0, the output is 1. Then having known the fundamentals of the bits, that is the binary digit, and the logic gate, we can now extend our knowledge of the classical computing to quantum computing. So classical computers consist of wire and the logic gate. So the wires are used to carry information around the circuit. So while the logic gate performs the manipulation of the information, converting it from one form to another. Then for quantum computers, a quantum bit is qubit. So it is both similar and a little bit different from the classical bit in some way. So it is similar because the quantum bit can also take the two possible states, 0 and 1. So just like the classical bit that has states either 0 and 1, a quantum bit also has state, and the two possible states for qubit, that is the quantum bit, are 0 and 1. So you can see the vertical line, and you can see something that represents the angle. So that symbol is called ket, K-E-T. So the difference between bit and qubit is that qubit can be in state other than the usual 0 and 1. And it can be done when we have superposition, or when we have the linear combination of the two possible states. In classical computing, we make use of bits. In quantum computing, we make use of qubit. In classical computing, we make use of the Boolean algebra. In quantum computing, we make use of the linear algebra. So if we have two states, 0 and 1, then there is possibility to combine the two states together linearly. And that is what makes the difference between the classical computing and the quantum computing, due to superposition. So we can now represent the possible state by phi. So we have psi is equal to alpha, then state 0, then plus beta, state 1. So alpha and beta can be complex numbers. So if you still recollect, a complex number z can be represented by x plus iy. So while y is the complex part, then x is the real part. So the special state, 0 and 1, are called computational basis set in quantum computing, and they form the orthonormal basis for this vector. So you can see that if you have an atom, for example, an atom can be excited, okay? So when the atom is in the least possible state, so the least possible state is what is called the ground state. So when the atom is excited to another level, which is the excited level, so it means that an atom can possibly occupy two spaces, the ground state and the excited state. And that is why qubit can be represented by, it's just a picture. It can be represented by the two electronic levels in an atom, that is 0 and 1, representing the ground state and the excited state. Now, when you have two states, that is the qubit represented by state 0 and 1. They can be combined together. And because in the combination, it is combined linearly, you have the state phi is combined as alpha state 0, then plus beta state 1. Then the alpha and beta are what is called the amplitude, because the state has to be normalized. And in fact, that is one of the properties of qubit. Okay, so that means that if the coefficient, which is also the amplitude, if you take the square of the coefficient, okay, and add them together, then it will give you 1. So what that simply means is that for qubit, a qubit can make a system to have a total probability of 1. To have a total probability of 1. So we can also make use of the Dirac notation. So in the Dirac notation, we have bra and ket. So the ket represents the two possible states in using the quantum bit, the qubit. So the two states can be visualized as the north and the south pole of a sphere of a unit radius. So the visualization is what is called the Bloch sphere. So in the Bloch sphere, you have the two possible states that can be occupied. However, it is possible to have more states being occupied. So we follow the normal physics convention. So you can see that the x-axis is coming out of the page. So while the y-axis points to the side and the z-axis is oriented up. So from the Bloch sphere, whose radius is 1. So 0, the state 0 corresponds to xy, that is 0, 0, 1. And that of 1 corresponds to 0, 0, minus 1. It is minus 1 because of the rotation, okay? So just like you have a logic gate, you can also have multiple qubits. In the multiple qubit, just like you have 2 classical bits, it is also possible to have a multiple qubit. For a single qubit, the possible states are 0 and 1. However, if you have 2 qubits, the possible states can now be 0, 0, 0, 1, 1, 0, and 1, 1. And they are denoted by the 4 computational bases, which is denoted by 0, 0, ket, 0, 1, ket, 1, 0, ket, then 1, 1, ket. So a pair of qubits can also in superposition of these 4 states. So the quantum state of 2 qubits, it involves a complex coefficient called the amplitude. So the complex coefficient can be alpha and beta. So just like you have the logic gate as a physical gate, then it is also possible to express quantum system having 2 distinct states as qubits. For example, if you consider photon, a photon is it carries a photon, like I said, is a unit of the energy. So meaning that a photon can be polarized. So when it is polarized, it means that it can be in vertical position and the horizontal position, or can also undergo superposition. When you have trapped ions, ions are atoms that are not in the neutral state. So when they are trapped, it means that they are being entrapped by the electric field. So when they are in electric field, when the electric field is passed through ions, it means that it is trapped. And when it is trapped, it implies that it forms a qubit. Then you also have cold atoms. So cold atoms for a neutral nuclei. For a neutral nuclei, it can also undergo spinning. Then we also have nuclear magnetic resonance. So for nuclear magnetic resonance, it undergoes a property of what is called a spinning. So a nuclear atom can be spinned when it passes through magnetic field. Then you also have the quantum dots. So for a quantum dot, you have an electron that is being captured, maybe on a super conductors. So the area where it is being captured can also undergo spinning. Then lastly, we have the super conductors. So a superconductor allows conduction of electricity, even at zero resistance. So meaning that if you have a superconductor, which allows currents to flow through them, even at zero resistance, then it implies that the superconductors can be allowed to move through electric field. So in that ways, it also forms a qubit. So just like you have the logic gate, we have quantum gate. So quantum gate acts on qubit, just like logic gate acts on the bit. So the quantum gate, just like the logic gate, it's transformed the state of a qubit into the other state. So we have the example. So you can see the quantum gate. The quantum gate is also being represented by unitary. It's also called the unitary gate. Okay, so U represents unitary. So if you have the state 0, which is being also undergone linear combination of alpha 0 then plus beta. So you can see that the alpha is complex in nature. That is a complex number. So while the beta is real, then that is for state 0. Then for state 1, the alpha is real number. So while beta is the complex number. Because in qubit, when it undergoes a linear combination, it has to be normalized. So meaning that the amplitude, which is the coefficient, has to be normalized. So the quantum gate will now perform operation. That is, it will transform the state of a qubit into other state. So a quantum state is linear. So that's one of the properties. That is, if you have a unity grid that is acting on the possible state, it can be expressed in that form. Okay, so we have alpha and beta that must be normalized. So for them to be normalized, alpha squared, which is alpha multiplied by its conjugate. So alpha conjugate alpha is alpha squared. So if it is possible to find the conjugate of the amplitude in such a way that the total probability is equal to 1. So the original state can also be normalized to now give us alpha squared plus beta squared is equal to 1. So if you look at the unitary gate that we have considered, that is the quantum gate that is undergoing normalization, it also proves that the total probability a quantum state can found itself is equal to 1. Thanks for your attention. Thanks for listening.
Oh,
True.
Your next one. So do we have any questions for Dr. Kunche? Okay, since we do not have any questions, we'll be taking a 5-minute break and then we'll return in time for our next speaker. Thank you. So please stay tuned and be sure to join us again in 5 more minutes.
Thank you.
I'd just like to comment that we appreciate Doctor. It's very simplified, and we appreciate we can have the material.
Yes, thank you.
Okay, yes, the material will be made available to us towards the end of today. We have we are collating all the material, so by the end of the program, everything that we've done will be ready. Thank you all so very much. So we'll be on a 5-minute break so that we can take pictures and attend to our guests. Then we'll get back to the next speaker next session. Thank you so much for joining us.
Can I quickly ask, can you still hear me?
Yes, I can hear you.
Yes, I sent a message to you that I would like to invite some like a Q Nigeria group to my talk. I'll be like I'm the next speaker. Yeah, okay.
Yes, I saw it. I was going to reply you during the break, but no problem.
Okay. Thank you.
Victor didn't say anything, but I think you can share it. Well, there's no monopoly on the event so far, so I think you should be
Okay.
free to share it. Yes.
Okay, thank you.
No, not yet. All right, so we'll be back in 5 minutes. Thank you. Hello. So we're back online and we're ready for our second speaker for today, Mr. Ibukun. So, sir, please take the floor away. We are ready and we are ready to listen to your presentation.
Okay, thank you. Let me try and share my screen. Give me like a minute, please. So, yes, I'll have to share my screen and good. I think that's good morning, everyone. Can you all hear me clearly?
We can hear you, but you could please be a little bit louder.
Oh, okay. How about now? Is it better now?
Yes, it's better now.
Okay. Once again, good morning, everyone. And I want to thank the coordinators for inviting me to give a talk at this year's IBM Qiskit QFF. And today, first, my name is Ibukun Adisa. I'm a PhD candidate at the University of Maryland, USA, and I'm also an IBM Qiskit advocate. And also, I am part of a group, a quantum computing community in Nigeria called Q Nigeria. Specifically, I coordinate the Q Talk where people give talks on quantum related subjects. So I'm trying to look for, there should be, yeah, I guess I can just do this. So today I'll be giving a talk on superconducting qubits, specifically quantum computing with superconducting qubits. Since this whole thing is being organized by IBM and the quantum system they use is based on superconducting qubits, I thought it would be nice to just introduce people to what superconducting qubits are. And since most talks are going to be a bit theoretical, and it's hard to, especially for the introductory part of quantum computing, it's hard to like see a talk that talks about like the experimental part and not just the theoretical part. And so that's what I want to use. I hope to do today, at least introduce people to what superconducting qubits are, how they are controlled, how they are measured, and especially what the back end of what you'll be doing for the whole IBM Qiskit QFF is going to look like. Basic outline, first I'm going to give an introduction to what superconducting qubit is, what quantum computing is, etc. And I'm going to talk about moving from front end to back end. So I guess when we get to the point, I will explain better what I mean by front end and back end. And also, yeah, and also I think I'm going to then dive into the back end, getting our hands steady. What I mean by getting hands steady is what is actually being done in the lab, the experimental lab that use superconducting qubits. So first, I'll start the introduction by taking a quote from what Google released on December 9, 2024, when they released their quantum system Willow. There is specifically some lines of statements that kind of resonates to me, like kind of summarizes why most of us are in this field. and it reads, we've pitted Willow against one of the world's most powerful supercomputers with a random circuit sampling benchmark. The results are pretty surprising. By best estimate, a calculation that takes Willow under 5 minutes would take the fastest supercomputers 10 to 25 years. That is a 1 with 25 zeros, or a time scale way larger than the age of the universe. And I think this kind of summarizes the interesting thing, and one of the main reasons most of us are interested in the quantum computing field. So I think I should also note that it's about 6:20 a.m. here. So I just woke up not long ago. So if my voice is somehow, I'm still trying to like adjust to my situation here, and it's kind of like cold also. So please bear with me till I warm up and I get accustomed to the whole thing. So back to what I was saying. This kind of summarizes why we are all interested in quantum computing. That there are some interesting problems that we can solve faster with quantum computing. That even though you might be able to solve them with classical computers, it will take a longer yet, which makes the solution even impractical. So guess the main thing about this talk is how is this being done exactly? What is ReLO? What is the superconducting? Since Google also uses superconducting qubits, what is the quantum processor behind everything that we see, behind every result that we get? So basically, that is what I'll be talking about. But before that, another basic introduction is what is quantum computing. And in summary, it's just using the laws of quantum mechanics to solve hard problems that are not practical, that are not easily solved with even classical supercomputers. They, like I said earlier, they might be able to solve them, but it's not going to be practical. You are not going to be even available when the result comes out. Then to do that, you need a quantum system. And the quantum system is what we call a qubit, which stores the information and allows us to do computation. So I guess I am assuming everybody is familiar with quantum mechanics. At least I guess it's the science of using science of matter and energy on the subatomic levels. So since the main thing I want to get across for this talk is to introduce to the experimental side, at least the practical implementation of superconducting qubits. I'm going to kind of like rush through some theoretical parts and briefly introduce some things. So what we have here is a typical quantum circuit that contains many things that come together to get the result, the kind of results that we want. So for this specific quantum circuit, that's some key parts. You have the qubits, which is the quantum system that we use to perform computations on, and we read out. So for example, this quantum circuit has like 4 qubits. Then we have quantum gates, which are the quantum operations that we use to manipulate our qubits. And then all of them together, they come together to perform some specific task, which we can call like quantum algorithms for that specific task. So for this kind of circuit, it creates a maximally anti-algorithmic state. For this talk, you don't need to know exactly what this means, but the message here is to get the final results that we want, there are many moving parts that we have to control and we have to know. And so like we need qubits to perform computations, and we need quantum gates, which we use to manipulate the qubits, which are the quantum operations. And everything all together is to the end goal of performing a specific task or implementing a specific quantum algorithm. And then briefly again, why we're interested in quantum computers is because there are some problems that are very hard to be solved with normal classical computers that we are all used to. And I guess the idea is that the world we are in is quantum in nature. To simulate a quantum system, to simulate a quantum world, you also need a quantum system. And that's why that's why we are trying to build quantum computers. So for example, some interesting problems that we can solve with quantum computers include like nature simulation, again, to simulate a quantum world, which is quantum, our world, which is quantum in nature, you need a quantum system. Then some other problems like search and optimization, factorization, etc. And I also want to point out that with quantum computing or with quantum computers, they are not meant to replace classical computers. And in fact, at least to the best of our knowledge and to what we know so far, we, like individually, we're not going to have quantum computers in our home. Maybe someone smart comes, like in the nearest future, someone smart comes up and figures out a way that we can also have quantum computers in our home, the way we have our laptops. Maybe that will change. But for now, the best way we know how to do these things, we are not going to have a quantum computer, like a personal quantum computer. We are going to use access some quantum computers and work together with kind of classical computers. So quantum computers, classical computers are not going to replace quantum computers, but to work alongside with them so that we get the end goal that we all wish to, which is like simulating nature and solving our problems. So yeah, so from backend to from front end to backend. The front end, I'm using this graphics from IBM Qiskit to kind of explain what I mean. From the front end part is, I guess, what most of us that will be working in the quantum computing space, what most of us will be interacting with. So you have your laptop, you have your Qiskit like a quantum programming language, and you run some circuits. You can also send circuits to like the IBM systems on cloud, and you get your results. So that is basically the front end. I think you are going to go for this for first. You are most likely going to go through some notebooks and some hackathons to run some circuits, and I think through that you can also send some of the job to real quantum system to get real results. So what you are actually doing when you send your it's called job in Qiskit, but when you send your circuits that you want to simulate and get that or your algorithm, what it does, it goes to some control system like control electronics, and what they interpret what you send to pulse sequences that interact with your quantum processor and send the result back. Most people are not going to have any idea of what this is and how it's been done. But because it's rare to see talks like this unless you are in the field, that's one of the reasons I said at least to let people know what the whole backend is, but not the whole, because I'm not going to cover everything, but at least to introduce you to what is happening, what is being done, what these consequences are, and specifically, this is a quantum system within IBM, what everything is doing. In general, what people would call a quantum computer is this dilution fridge, like this thing, this cylinder here. But as we'll see in the next few slides, the quantum processor, which is actually the quantum computer, is just something tiny around here. And like I mentioned earlier, this whole thing, let's say it's the quantum computer, is not going to like replace the classical computers. These are some classical systems, classical computers that are used to talk or work with the quantum processor in this dilution fridge to get your result out. So they are going to work hand in hand to get the end goal. So like I also mentioned, this is really big. You're not going to have it in your basement or in your house. You have to like access it in the cloud with from I guess companies that have these quantum systems. So like in summary, we are going to move from the front end to the back end and understand what all these are, what they are doing, and how the result had been transferred, how your commands are being controlled to bus sequences, how they interact with the quantum processor, and how they are measured. So since the big thing about this talk is about qubits, even though we are going to be focusing on superconducting qubits, I think I thought I joined late to the last talk, but I also think I think professor that gave the talk mentioned also some other types of qubits that we have. So briefly, I'm also going to like list them. There are also other types of qubits that we have. The main thing is we want a two-level system, a two-level quantum system to make a qubit. And many people have ideas on how to achieve that because each of them, they have the advantage and disadvantages. But so we have neutral atoms, we have trapped-ion qubits, we have photons, we have quantum dots, we have NV center qubits. But since it's an IBM Qiskit advocate and someone that works directly with superconducting qubit, I'm going to focus on this part, which is superconducting qubits. What this is? When you see something like this, what exactly are they trying to say? What does it mean? So again, briefly to just like motivate us and to maybe catch our attention and get to draw us to what I'll be talking about later. This is a quantum system or quantum processor from IBM. This is something similar. It's also a quantum processor, but from my lab at UMD where I work. And so like I mentioned, this is where your quantum, this is where the operation is being done, the real operation is being done that you want to read out. And the qubit, the main qubit that we all talk about is not, so this is a 7x7 chip. Mostly you have a 7x7 chip, you have one each chip, and it is about 7x7 chips are really common. So 7x7, I mean 7 millimeter by 7 millimeter. So think about what a 7 millimeter is, which is less than 1 centimeter. So these are really tiny. Even though this is tiny, you still can't see what the qubit is because the qubit is somewhere around here. You have to like magnify to like nanometer level before you can see the qubit. So for a superconducting processor, they look something like this. You have this pattern on some wafers that you pattern your system in, and the main qubit that we like a superconducting qubit. I'm going to explain this later. It's this junction here. This is the Josephson junction. I'm going to explain what this means in the next few slides. But this is your actual qubit. Everything else, this whole thing, dilution refrigerator, is to control the environment for this qubit. And everything you have here, this is a picture I took yesterday, these two ones. Everything you have here, even though this is kind of messy and it's not like clean as the one you will see with IBM, all the wires here are how to control and read out these qubits, this tiny thing that we can't even see. So yeah, so then I think we can now move on to discussing superconducting qubit, how we achieve that. To kind of like give a theoretical background and motivate, try to understand how we get to the level of implementing a superconducting qubit with solid state system. I'm going to I think the physics students here, we already know what this is. If you are interested in some of the theories I'm going to discuss now, you should go to chapter 2.3 or section 2.3 of this book. This is one of the most popular books in a physics undergraduate course. And um, yeah, I'll be discussing a quantum harmonic oscillator. Then before that, I will first discuss simple harmonic oscillator, then quantize and move to a quantum harmonic oscillator. The reason why I'm doing this will be clear when we get to the later slides, but just bear with me and stick along for, I think, for the next 2 to 3 slides, and you'll see the reason why I'm going through all this. So a 1D simple harmonic oscillators. In general, harmonic oscillators are systems that are really popular in physics because they have a lot of things they represent and they have a lot of physical interpretations. So an example, to be concise, an harmonic oscillator is like a system oscillating around equilibrium position, like you have a pendulum or a mass attached to a string. Generally, you have the kinetic energy to be half mv squared, or x dot, which is the first derivative of the position, which gives you the velocity. Then you have the potential energy. Then you can calculate what the Lagrangian is. So I'm not going to talk about what is a Lagrangian. I think that's the whole course in physics and classical mechanics, and to say I want to explain that here, it's going to take a lot of time, and I think you don't really need to understand what it is. The message I want to pass with this talk doesn't. You will see the reason I'm going through all this in the next few slides, so you don't. Then it's just like for formality. Then you use Euler Lagrange equation to calculate what the equation of motion is. As you can see here, the equation of motion tells us the combining all this, you get harmonic oscillator that oscillate at frequency root k over m. Then also you can calculate what the Hamiltonian is, which is total energy of a system, then which is the kinetic energy plus potential energy. So the reason why I kind of show this is to kind of motivate how we implement harmonic oscillator in a solid state system by using a quantum circuit that consists of a capacitor and an inductor. So where this is I is current, V is voltage, and flux is the integral of the voltage. So to do all of this, you need to know how all these relations between the voltage, inductor, current, and capacitor, and the flux and the voltage. So exactly, we can do the same thing and calculate what's the kinetic energy and potential energies for this circuit is. And here I'm using flux as the generalized coordinates, just as we've used x here. Then we can do exactly the same thing. Get the Lagrangian, calculate the equation of motion. Here the equation, here we can see it's an harmonic oscillator, oscillating at frequency 1 over root LC. Then you can also get this the Hamiltonian. As you can see here, it has the same form of what we are mostly used to. You might have gone through this calculation, especially if you are a physics undergrad, but to people that are not really familiar, it's just to like see that this kind of solid state system implements an harmonic oscillator. You can see if you can replace your mass with the capacitor, and K it's like the spring constant with 1 over L, and phi is x here, so you get exactly the same thing. So to move into a more familiar form, you can transform this. X dot is velocity, mv is momentum. You can write the Hamiltonian in this form. So for the purpose of this talk, the next thing, most of the theory or some of the things I'm going to say here, you can go into this paper to read more. It's a very important paper for especially me. I always have the tab. I always have it on my Adobe Reader because there are many things that I just go back there to look for the formula or for the explanation. So then what we want to do is to quantize to what we went through in the last slide. And what I mean by That is like your simple harmonic Hamiltonian. You have the momentum and the position operator. You also have the charge and flux here. What we mean by quantization is just turning this, the coordinates, turning them into operators. So easily we just everything here for more information you can find in section 2.3. So, and what we do, since these two are the same thing, they represent the same, like now they are quantum harmonic oscillator. I'm going to just use one of them since they are exactly equivalent. Then we can rewrite this in form of the charge operator n, which this is the same. You don't need to like go from here to here to get the final results that I'm going to show. But yeah, the main reason I'm showing this is now we can rewrite our the Hamiltonian in form of the raising and lowering operator. This figure specifically is very popular for physics undergrad. And what's the reason, and for people that are not traditional physics students, what this operator mean is like when a raising operator acts on a quantum system, it transforms it to the next system, to the next state when it's act on. But when a lowering operator acts on a state side, it drops it down to the nearest lower state. And then we can get what the energy level for this kind of system, for a harmonic oscillator energy level, the energy of each of the levels En to be this form. And then the reason why I'm going through this is because, like, for a quantum harmonic oscillator, you can see the energy levels are equally spaced. So when you take two consecutive energy levels and you get the energy difference between them, you can see it's always h bar omega, which means these are equally spaced. So we can represent this in a more formal way by showing the energy levels. These are the energy levels, and the difference between each energy level is the same. So what we really want is a two-level system. We want to have we want to compete with 0 and 1 to form our qubit. But for a quantum harmonic oscillator, since all the levels are equally spaced, you cannot use this because the kind of operation that takes you from 0 to 1 also takes you from 1 to 2, takes you from 2 to 3. So you don't have an isolated qubit. So so that's why this doesn't really work. So what we need to do, we need two-level system. We need a two-level system that we can isolate. It doesn't have to be like, the system doesn't have to be just two. It can have three systems, but we want, instead of it being harmonic, we want it to be anharmonic. What that means is that the transition from 0 to 1 is different from the transition from 1 to 2. And that is what is being done with superconducting qubits. And how is this being done is we replace the inductor here with a nonlinear inductor, which is called a Josephson junction. It's a nonlinear dissipationless inductor. And what that does is, the Josephson junction, to be specific, is just like when you sandwich a superconductor insulator and a superconductor. This is a Josephson junction. And because, like, I mean, aluminum at about 1.2 Kelvin, it's a superconductor, then we get all the properties that we need to form a qubit. To be specific, we go from let's say, the quantum harmonic oscillator, the Hamiltonian, which has a quadratic potential, to a to a system that has a nonlinear inductor, which has a cosine potential. And this is the main difference between them. Now we have a source of nonlinearity. And what that does is that when you calculate the energy difference between for this kind of system and this kind of system, here you have between two consecutive energy levels, they are the same. You have a constant value, but here it depends on n, so it's no longer constant. And the physical interpretation of that is, for a quantum harmonic oscillator, you have equally spaced, but because of the cosine potential that we have here, this is kind of like spaced. And what it does is that it changes the energy difference between 0 and 1 from 1 and 2. As you can see, as you go up, the spacing between two consecutive states reduces. So with this, and if you get what's for example, from 0 and 1, the difference between them, it depends on EC, which is a function of the capacitor in your system. So then by engineering it smartly, we can isolate these two. We can isolate 0 and 1 to form our qubit. And this is bread and butter of a superconducting qubit. To be to specific, now this is a computational subspace. You can isolate 0 and 1, and you can use that to form your qubit. And that's because the quantum operation that takes like a pulse that takes you from the ground state 0 to 1 cannot excite 1 to 2. It can excite 1 to 2, but you have to like go really crazy with your power. I'm going to show, I dropped some pictures that I'm going to show later on how this can also happen. But at least when you work at your reasonable region, you can isolate these two states unlike this. So this is exactly what forms your qubit. And for Google IBM, this is what they all try to do. Just introduce a nonlinear inductor to your system and you get your qubit. So now let's say we have a qubit. How do we read it out? Since we all know when you disturb a quantum system, you lose the information. When you measure it, you lose the information. But we don't want to do that. We want to know what the state of the qubit is without messing or disturbing the state of the qubit. And it's just like a simple analogy is like for a quantum circuit, if you've not been introduced to it yet, you learn about something called ancillars that you can use to like infer or get the state of the qubit without disturbing the state of that exact qubit. You use an extra qubit to infer the state of the qubit. For measurement, what we do is, funny enough, we couple the two. The system that we don't like because because of equally spaced energy levels and we can't use it as a qubit, we couple it with a qubit. And if you've gone through quantum optics, you will know about James Cummings Hamiltonian, which kind of describes when you have a two-level system that is coupled to a cavity, the Hamiltonian is given by this. So you have the first term, which is the cavity or resonator term, the second term, which is your qubit term, and the third term, which is the interaction between them. So what this is essentially saying is this is lowering A and A dagger, the lowering operator for the resonator, and sigma plus and sigma minus are the lowering and raising operator for the qubits. So when your qubit loses, when your cavity loses a photon, your qubit gets a photon. When your cavity gets a photon, your qubit loses a photon. But then this also doesn't really describe how we measure, but there is a good limit that when you have these two systems copied together and you have the frequency, the transition frequency between like omega r or h bar omega r and h bar omega 0 far apart than they are coupled. G is the complete constant between these two. When they are far apart than they are coupled, you go into the dispersive limit. That is, when you take this approximation that omega q minus omega r is far greater than G, then you can transform the Hamiltonian into the dispersive Hamiltonian given by this. And what this is saying is now, like you can map from here to here. Now, what you go from omega r being just for the cavity to omega r being dependent on the state of the qubit. So since sigma z is a qubit operator, what's essentially what this is saying is when the qubit is let's say at state 0, your resonator changes its frequency. When it's at state 1, it changes its frequency. And the amount of changes when the qubit, the amount of shifts you get when the qubit changes is this chi, which is the dispersive shift. And so to be specific, let's say you have a quantum harmonic oscillator or a cavity or resonator to be precise. When it's not copied to anything, this is the kind of response you get, which is saying now you are on resonance with the resonator at omega r, right? But when the qubit is at the ground state, the resonator frequency changes to omega r plus chi. When it's at the excited state, it moves to the opposite direction at omega r minus chi. This isn't always true for like the direction or the position of these two. Also depends on what the sign of chi is and what's the frequency of each of them is. But the biggest thing and the true thing for our system is when the qubit is at a particular state, the resonator assumes a different frequency from when it's at like let's say when it's at 0 and 1. So that in short is how you when you couple the system and how you measure your qubit. So this is another example of a quantum operator that has a qubit that I think we convey the message that I just passed. So what we have is a transmission line. So you send your signal in and you read it out. And from that, you know what the information of all your system, of what information of your system is. For example, this sending a signal out at a frequency from 6 to 7 gigahertz, because these blue things are all resonators and they have their own frequency that is mainly determined by the length. So if they have different length, they have different frequency. And I think I can maybe, if we have time, discuss how some of these are engineered, because these are the things you deal with when you are actually working in the lab. So now you have, as you can see, this is the actual measurement done on this device. Now you have three signals, three resonance at each of the frequencies. So you have your transmission line, you have your resonator. This doesn't have a qubit. So this is a qubit. These are the capacitor parts, and this small thing here, which I've magnified here. This is, I think, about 100x on viewing under microscope. That's when you can see what the qubit is. This is the qubit part. This is the resistance junction. These are the resonators. When you send your signal in, you can get what is happening to the qubit by just monitoring what these resonators are saying. So you get the information about the qubit by checking what the resonator is saying, and that is essentially how our qubits are read. The red things here are flux lines. So if you have so we are not going to discuss that today, but if you have like you can see here, this is a junction, this is another junction. If they are in a loop, this is the flux line. You can use that to tune the frequency of your qubit. So that is also like useful and needed in some computations that I don't think we are going to discuss today. So essentially, as a recap, you have your qubit, you fabricate your qubit, you make it, then instead of probing it directly, you get your information about the qubit from the resonators here. And so there are different designs that you can have. This is what we call a Hanger resonator. This is a transmission line. You have your input signal in, you measure the same signal out, but based on the interaction due to capacitive coupling between the resonator and the transmission line, you can infer what is going on. Another method that you can also use is like you have a transmission line, you connect it to the resonator. So there are gaps in between here. So gaps here, and there's also like a gap here. And connect it to the other end to read out exactly what is going on. And depending on the kind of depending on the which of these that you adopt will depend on the kind of results that you get. For example, Hanger resonator, you have a dip, and for a transmission kind of like connection, you have a peak. So so let's say now you have your qubits and you measure it. The first things that you do is you check I was planning to like go through how you make a qubit and how you measure and how what's it called, how things are done, because that's a completely different area. There are people that are doing their PhD in that kind of area because measurement is also hard. But due to like if you have a qubit connected to a resonator, you can easily check if your qubit is alive. That means that is your qubit is working and there is no qubit. And what you do is like you increase the power of the signal that is going in and out. But when there is no qubit, you just get a resonance because there is no coupling, there's nothing changes. You just get a direct tone as the frequency of your resonator. But when there is a qubit that is coupled to your resonator, at some point, you can see the resonator frequency. It starts to shift. When it starts shifting, that's when you know, as you can see here, when it starts shifting, that's when you know now I have a qubit coupled to my resonator. So when you have a system where there is no qubit coupled, you get something like this. When you have a system when there is qubit coupled, you get something like this. Sometimes when you fabricate, you mess things up and your qubit is not alive. So basically it's going to act like this. So in our lab for PhD students, after you have your device in the fridge, the first thing you want to check is are your efforts in vain, or you have something to work with? So you check if there is a qubit and there is no qubit. And so I guess one of the most important things, if you are going to go through the theoretical aspects, you have like almost everybody, they say when you create a quantum system, your qubits are initialized to 0. And why is that? Your qubits are always initialized to 0. You always have a ground state. And that is the reason why you need this. You need to cool down to a very low temperature such that that is like the minimum temperature you can get to. And we know from quantum mechanics, your minimum temperature gives you the ground state. And then that means when you cool down your whole system, you are initializing your qubits to be in the ground state. So some people ask questions like, since you want your Josephson junction, which is a combination of aluminum, a superconductor, insulator, and a superconductor, but the commonly used superconductor is like aluminum, but the critical temperature is 1.2 Kelvin. So why do we need to cool down to 15 millikelvin? Because many systems you need to cool down to 15 millikelvin to get your system in the true ground state, or to make sure your system, your qubit is in ground state. And the reason is that you have for this area, you have some specific region you want to have your qubits to be in. So qubits typically you want them to be, I mean, it depends on the lab on what you want to do, but usually you want them to be between 4 to 5 gigahertz, and you want your resonator to be around maybe 6 to 7 gigahertz, so that they are also far apart, like I mentioned earlier, the dispersive limits. You want them to be far apart than they are combined. So let's say the qubit is at 5 gigahertz. That corresponds to so the transition frequency of the qubit is 5 gigahertz. That corresponds to the temperature of 0.24 Kelvin. So even though you say, okay, you want to cool down to one Kelvin just for you to get superconductivity with aluminum, that temperature is still greater than the transition energy of your qubit. So at that kind of temperature, you can still populate, you can still take your qubit from 0 to 1. You can still take it from ground state to excited state. So in such system, your qubit is not truly in the ground state. So what you want to do is that even after you've isolated your system, so you've isolated your qubit from any disturbance, any environmental disturbance like vibration or magnetic fields that can change the frequency of the qubit. Because some of the things this also does is like isolate your qubits. You also want it to be really, really cold so that you can get to the true ground state. And what you want to do is you want to make sure the thermal energy at where the qubit is very, very low compared to the transition frequency of the qubit. So this is the reason why most systems, they want to cool this down to 50 millikelvin. In this kind of system, another beautiful engineering and complex thing is going on to get to that kind of low temperature. As if you don't know, this kind of temperature is even colder than the outer space. So the coldest temperature you will see on Earth is going to be inside these dilution refrigerators. But then usually it's easy to say, oh, apply X to 0, apply Y to 0. What does it, what are you really doing when you want to apply a gate? What does it mean? So when you send the kind of circuits to like IBM quantum computer, how does it apply X gates? How are X gates done? And if you've seen, sometimes you hear them say, our gate is the fidelity of the gate, which means that if you want your gates to perform X, it also perform X, because the quantum system is delicate in nature. Sometimes you want to do something, it does something else. To perform gates, what you are really doing is microwave pulses. You are sending microwave pulses. So you have this system. These are you can't see anything, but just take it. This, for example, this thing that you have here is a microwave generator. It generates a signal at a particular frequency, and that is exactly how you implement your quantum gate. What you are doing is that you are sending a microwave pulse with a specific amplitude. These are pulses. It can be a square or a Gaussian pulse, so you don't really need this. It doesn't really matter, but for the actual implementation, this also matters. You have a pulse with an amplitude, a frequency, the timing of the pulse, and the phase. Sometimes for between X and Y, the difference here is, so I think for X, phase will be 0, and for Y, it's going to be pi over 2. So to calibrate your system to apply these gates, this is what you are doing. You are trying to find, you need to like calibrate your system and find what is the right A that you use, that you say, okay, this microwave generator, give me a signal with strength A, frequency T, and also I'm going to apply that for time T. This thing, when you send your system and say, I want to apply X gate, that is what they calibrate. They send a microwave pulse into the fridge at some specific thing that you've already calibrated to know how much time you need to apply a particular frequency to get the X gate. And this is a simple sketch of what is being done. This AWG here, arbitrary wave generator, gets you what the pulse is, and this LO here, or the RF, gets you this sign thing. You send it to your system. You have some circulators, you have some amplifiers, you also have some. So this is another a different thing entirely. That it's like what people spend years trying to figure out so that we can measure. And this is a simple sketch. So you can see G is ground state, E is excited state. So what we can do is, after we cool down our system, I can measure. I'm not going to apply any gate, but I'm just going to like probe the resonator and see and read out what. So I think this is about 5,000 or 2,000 shots, and read out what they said, read out what I get. Since I'm not applying any gate and I've cooled down to about 15 millikelvin, if everything works fine, what everything you're going to get is going to be in the ground state. But because like it's a quantum system, is delicate in nature, even though it's at 15 millikelvin, there are still some quasi particles, there are still some things that disturb the qubit. You can see there are also some I'm going to show another plot that shows this really well. You can still see also some populations here. So even though you have initialized everything in a ground state, you still have some excited state population. And also when you apply X gates, it changes, it shifts the frequency and it changes the IQ component of your readout. So this is excited state. So this is 0, this is 1. But when you do exactly what you want to do. You can also see, even though you want your system to be in E state, there are some times where they are in G state. If in an ideal system you want these two, you don't want any overlap. But in all systems, or like in practical, at least for now, you still get some leakages. And also this is also due to like the timing or the coherence time of the qubit. So here you want to know what the qubit transition frequency is, so that when you send that pulse, it only takes your qubit from ground state to an excited state. What you do is, after you know what your resonant frequency is, then you look for the qubit. As you see here, at minus 20 dpm, at very low, so 5 is way greater than minus 20, you only see so this is the qubit. This is a measurement that tells you have something here, you have a qubit here at this particular frequency. But when you also increase the drive of the tone, you populate the second excited state. So even though you have like say you want to isolate two energy levels, two energy levels for your qubit to get for 0 and 1. When you also drive too hard, you populate the excited state. You populate higher excited states. Then from here you get a, which is like I can say about minus 20 here, and you get the frequency. This is not exactly A, but for this, let's say that is it. Specifically, what we usually do is there's also like a factor that multiplies this whole thing, which is about minus 20. So in practice, what you usually do, you set this to a particular number. Now that you have your frequency, then you can calibrate the time for the pi pulse, which is X. So what you usually do is you apply A sine omega, the frequency, for different times. So for time t equals 0, nothing happens. So you are still in ground state. You apply for different times, and the idea is that at some time that is equivalent to your pi pulse. Then as you also rotate the qubit around, like you can imagine a block sphere, you start to go back to the ground state. So when you get this kind of measurement, you can calculate or fit your graph and see at what time do I need to apply this signal of a frequency and amplitude to take my qubit from the ground state, the lowest um, um, to the lowest IQ that you get, the lowest point, to the excited states. Then so now you extract this time, now you have what your pi pulse is. So that is exactly how you get your, let's say, your X gate. So when you send when you send something to IBM quantum computers, when you say apply X, this is what's there. It already has, since they know their system, they would have already calibrated it. They know if you want to apply X, if you want to apply Y, they know the time, they know the frequency of the qubits, they know everything. So that just talks to the classical computer there, and it sends out the right pulse at the particular time. So another measurement you can do is to calibrate your qubit coherence time. That is in a perfect system, what we want is, like, after we go from 0 to 1, we want our qubits to stay at 1. Right. So I have like a quantum circuit. I apply X equals X0, which takes it from 0 to 1. But in practice, it doesn't stay at 1. It decays back to the ground state. And what you want to do is to calibrate your T1 time, which is like on average how long it takes for your qubit to go from, so after you excite, how long does it take to go from 0 to 1, 1 to 0. So for this particular qubit, it's not it's good enough for the kind of computation I wanted to do, but it's not good enough in general. So this is like 20 microseconds. I think the best time is about for at least for superconducting qubits about maybe it's of order of microseconds. It's of order of milliseconds. So what this means is the operations that you want to do, your measurements, the operations that you want to do, they have to be really, really smaller than this. So for example, let's say you want to apply a gate for 1 second, but while applying the gates, on the qubit, or while measuring the qubit already decayed. So you don't really, it doesn't really make sense. So whatever you have your coherence time, there are some people that are still working on having more coherence time, I think, and there are some other systems, like maybe trapped ion also that have, and maybe neutral atoms that have longer coherence time. So for superconducting qubit, the coherence time is still really low, but at this point, they're at a point that you can do computation with. So these are many considerations that you have to, many things you have to consider. And this again is like this is a ground state measurement. I have my system, in the ground state. I have already cooled down. Then I want to measure, I'm just measuring the resonator. So because since the qubit is coupled to resonator and they are cooled down, whatever you measure is going to be the ground state. But you can see here, even though it's cooled down, trying to measure, there are some other things that also excite your qubit. Excite your qubit. So everything should be around this blob. These are single shots. Everything should be around, yeah, this is 500 points. Everything should be around this point, but you have about 100 points that you measure your qubits to be in the ground state. And also when you excite your qubit, when you apply X, takes it from 0 to 1, you can see, or during measurements, because this is really small, when you are measuring, you also have to like measure really fast. When you are measuring, the qubit already decayed back to the ground state. So these are the things that these are the things that are being done for superconducting qubits. And yeah, so because we don't really have time, the general workflow in superconducting qubits, it's always kind of like follows this, and each of them is really technical and can be a little bit complicated to get to the final result. So you should you should appreciate what you the kind of results. So when you use IBM quantum computer, there have been a lot of work and a lot of time, effort, and money that's been spent. So before you even do anything, you know the kind of computation you want to do. So you have to design what your qubit is, what your resonator is, how many qubits you want on your chip, how many resonators do you want, how you want to measure. You do that with AutoCAD. Then after you're done with the designing, you have some theoretical values to kind of gauge what you expect the frequency of everything to be at. Then you simulate your system using ANSYS. From this we can get even closer results. So you design to be at a particular frequency, you simulate it with this software to see if everything is at the right if everything is at the right frequency. You can also use it to get the capacitance matrix. Um, since you can change the anharmonicity alpha of your system by playing with the capacitance of the qubits. You can also get this, see if what you design is in the range that you want. If it's not, you go back to the design to update it. Then you come back to simulation. When you are done with simulation, you see that everything's at the right spot, then you do fabrication. So fabrication is a whole thing itself. Um, it's a really big industry. Um, um, but yeah, I do this too. I do everything myself. So for the fabrication means you have a chip that is plain that doesn't have anything. You have to like,
Please,
am
can
I?
you speak louder, sir?
Oh, sorry. I hope people have been hearing me so far. Yeah, so you so from the design to the simulation, then you fabricate your device, you pattern everything, you make your Josephson junction, you make your resonator, then you package everything so that you can put this. So this is like the final packaging that you put into your dilution refrigerator. And like the design I showed earlier for the qubit, or for the quantum processor that has, I think, 3 resonators. You have your input, you have your output, and you have these 2 inputs to like control the frequency of the qubits. And what I mean by packaging is, so let me see if I can quickly go back there. So this is what your the device looks like, but you still have to like since you have to like make sure you connect to some conductors so that you can send a signal in, read it out, and send something inside of these two. So this is what you are doing here. So you have a PCB, you have this little tiny thing. This is really small. You also have to look on under the microscope. You have a PCB. So you have this wire bonded. So these are like small wires of small specific materials that you need to use to connect to each of the ports. So as you have these lines here, these are like transmission that you can use. Like these are ground, these are transmission lines. You connect the ground, you connect the transmission lines so that so that when you connect a cable here, it talks to the right spot that you want it to talk to. You note everything so that you are not sending a wrong signal, a wrong frequency to the wrong place. You make sure everything is right. Then after that, you close everything up to shield it. So since you have a way to talk to your qubit is in, or your quantum processor is in somewhere here, you connect everything together. You solder the wire bond. Now that you have your qubit or your device, then you can mount this. So after you mount, since this is when you are doing the fabrication, this is like a 7 by 7 millimeter thing. You have to hold it. You have to work with some acid to eat up some things. You have to do a lot of things. So while doing that, you can scratch up your system, and some scratch you can easily see under the microscope. When you view things under the microscope, you will see if you scratch something, then you have to like go back and start all over again for the fabrication. Sometimes you can spend months on this fabrication. Sometimes when you are really better, then you can spend like a week or so on fabrication. So after that, so even at the last stage that you are going to, this can take a lot of time. Sometimes it takes days to pattern everything up. But this really is kind of like the last stage that you go through to package your device. But also things can go wrong here. When you make a mistake here and you scratch your device, then you have to start all over again with fabrication. So let's say everything works fine, then you have to cool down to 15 millikelvin. That takes also about 2 days. Then you have to check if your qubit is alive. So maybe while packaging, you messed up with something, or maybe um, your connections are not right. Um, when you cool down, you check your device, and that can be really that can be really emotional because you've gone through all these stages, and you can't really say that your device will work until you cool down. So after you cool down, you see that your device is working, then you calibrate to get the frequency, the pulses. Then after you have everything, then you can now run your simulation. You can now run your computation. So that's like a general workflow for superconducting qubits. So here, this is from IBM. This is at this point, this is where the base plate here, the lowest point here, this is where you attach your qubits. Everything here at all stages, this has different stages that you go through so that you can get 15 millikelvin here. And so these are all lines. What you have here, these are isolators, some circulators, and I'm not going to really talk about them. But yeah, what you have here, you have some lines that are connected to these microwave generators, and you have some other things too that you connect to your qubits. You label everything. You know what you are controlling to get what you want to get. You send your signal out, and you send your signal out to the device, and you read it out to get your results. Then, if you are sending it to IBM quantum computers on the cloud, this is what is being done. They convert all your instructions to pulses. You send it to the qubit, they read out, and they give you your answer. So yeah, that's the end. I don't think I have a summary. So, like in summary, what is being done with superconducting qubit is you want to get a system, a two-level system that has two states that you can control. But doing that has a lot of things that are hard background. Yeah, I just spotted this. So what you have here is like a cylinder that you put in liquid nitrogen so that you can get this cool down to a particular temperature. Then something else kicks in to get it down to like 15 millikelvin. So this is not a tutorial to like teach you what how to get superconducting qubit, because each of the steps that are in like making everything work, each is a really big field that you go in and you can sometimes get lost. But it's just like introduce everybody to what is actually going on, what's a superconducting qubit. So when someone asks you what's a superconducting qubit, it's just like a connector, a nonlinear inductor with a capacitor to get an harmonic oscillator such that you can isolate the two energy levels. So that's, yeah. Oh, I hope I've not gone past the time. That's the end. If you have any question, please let me know. Oh yeah, sorry. Oh, I didn't see this. Yeah.
Okay.
Do people have questions, or I can stop sharing?
Yes, there are questions.
Okay.
But the one that's supposed to talk. Sit in.
Okay. Are there any questions from this end?
Questions.
Please ask the question.
Okay, there's a question. Okay, there's one online, and then there's one here. We'll start with the one online.
Okay.
So, Mr. Tiami.
So, Mr. Tiami, please,
Yeah, thank you, everyone. Good afternoon. And firstly, I want to the organizer of this year. I want to, thank Adisa for his wonderful presentation. Actually, it's a very nice one. My question is that have you been to the field of fabrication? You know, in Nigeria, we've not advanced to that level. I want to ask,
Yes.
have you been to the field of fabrication of quantum bit? And if you have, what are the materials? What are the materials and the process at which you've gone so far? And my second question is that at the diluted refrigerator, when cooling the temperature of a qubit,
Yes.
are we together?
Yes.
Hello?
Yes, I can hear you.
Okay.
Yes, I can hear you. Yes.
You know, qubits are very funny physical quantity. Suddenly, if the thermal energy suddenly change and it happens that it's greater than the qubit frequency, what is going to happen in the process of measuring or taking the readout of that particular qubit? Let's,
Okay.
for example, consider a two-level qubit, like maybe a single qubit, for example. In the process, when the thermal energy shoot up over the
Yes.
qubit frequency, what is the
Yeah.
consequences?
Yeah.
I
Thank
still have
you.
another question, but please let others ask their question, and maybe we'll be talking at the back door on some issues.
Yeah.
Thank you.
Thank you, Tamu. And I want to also acknowledge TMU from Q Nigeria Group. It gave a really nice theoretical background to superconducting qubits some time ago, and that's one of the things that prompted me to do this circuit. So yeah, I appreciate you for showing up, TMU, and thank you for your talk. And for the first question about fabrication, so yes, this is my work. This is what I did. I make the device. So for the device in our lab, if you have a project and you design a device for your project, you go through all of this yourself. So for my so for this specifically, this is for my project. This is what I made. This is the measurement. I made this Josephson junction, the device. This is part of the setup. This is part of the measurements. And this is my hand. I just took this yesterday. And yeah, so in some other labs, for example, I think MIT doesn't really allow their students to make the devices themselves because they have like a fabrication lab. So you just send your design to them and they make your device for you. But for us, we do everything ourselves. So for like the fabrication stage, you design, you simulate, and and I think you also asked a question of materials. So let me see. So for this kind of material, you have your tantalum. So that's like the material used for material. So you have tantalum on sapphire. The sapphire is the wafer. You have like a background. I don't think I really have the big picture here. So you have like a material which is like an insulator. Then you pattern your like superconducting material on it. So what you have here, the black thing is the tantalum. The black thing is the sapphire, or you can also use silicon. And then this gray thing or white things are tantalum. So another research area is trying to figure out which material, like in material science, which material is good for all these things. I think it used to be niobium that you pattern on sapphire or silicon. Then now most people use tantalum. And then for your qubit to say it's aluminum oxide, aluminum. So one of the things in like the fabrication stage is like if you see this after you go through, so the stage that you get this is different from the stage that you get this. And you can see there are some spots, there are some things here that you have to clean. And I don't think if you can see, if you can zoom really clearly here, after I made the junction for this particular device, the junction didn't work out where there was an error when I was patterning the junction. So I had to like start all over again. So these are the things you go through. And for the other question on what if the thermal energy exceeds the transition frequency. So that is why so at like let's say your qubit frequency is 5 gigahertz, you need at least a temperature of 0.24 kilo it's 0.24 Kelvin to be able to excite your qubit. But that's why we maintain this very, very low. So this is 0.0015 Kelvin. So at the time that you have your fridge cooled down to 15 millikelvin, you do not expect any thermal excitations. But still, there are some like I showed here, there are some things that it's disturbing your qubit. That's why you have these populations. So you don't, unless you average everything as so that the noise goes out, you don't really get a system that you have. Even if you check Google papers, you still have some things, even though their own might not be as bad as this, but you still have some populations that are not supposed to happen in an ideal system. So by cooling down to this kind of temperature, at least you are guaranteed that whatever excites your qubit is not a thermal energy, it's not from thermal energy. Yeah, once again, thank you for the question.
Okay, so we have a question from a participant over here, and
Okay.
I'll be giving the mic. So.
Okay, I thank you, Mr. Ibuku, for the very insightful talk and exposure, particularly the fact that this what you are doing, it's a great exposure to so many of
Thank you.
us. Um, I want to thank you especially for the presentation. Now,
Thank you.
I want to ask some questions. One, based on the fact that people who are listening to you here are not necessarily engineers or,
Yes.
or physicists. We also have mathematicians. And
Yes.
then there are so many of the terms that might require some clarity.
Yes.
Personally, from my understanding of your talk, you have shown how the circuits can be formed by the couple of whatever you have put together. And this actually goes into what the engineers would do in the actual lab practices, in constructing what a circuit will look like, apart from doing it by using simulations and what to do using Qiskit. Now,
Yes.
my question starts with the fact that what is the effect of the number of qubits that can be used to design a circuit? I mean,
Okay.
as it relates to the resultant frequency and the output, which is the end product of the device.
Yes.
Next question. Can you answer that?
Yes. So to quickly answer that, so let me start from like where is that? So this is like a 7x7 chip, and there is a lot you can't fit, like for example, this can't hold 1,000,000 qubits. So that's one of the reasons why we don't have a fault tolerant quantum computer yet that we can perform the kind of say factorization algorithm on. And so that is still in process. For example, I think IBM, as maybe Google, I think the number of qubits that they have the maximum number of qubits that you have on a chip, I think it's about 130 plus qubits. And it boils down to the fact that, so let's say this is a dilution refrigerator. Whatever you are going to put in here has to be as the biggest thing, it has to be as big as that's like the largest size it can be. And since these things, even though you have where is it? Even though the bigger part is like the capacitors that you need to couple to connect with your Josephine junctions to make the qubits. So imagine you want to have this like 1,000 of this on this chip. That is not possible. So it's still like a current research area that people are trying to figure out how to get as many qubits as we need to perform the computation. Some people are trying to do what is being currently done in semiconductor industries, that you have 2 qubits layered on top of each other. So let's say you can fit in, there are different sizes for the wafer. So this is 7x7. You can also have a 1x1 inch. I think there are still, I think, 320 millimeter, 3x320 millimeter chips. So some people are trying to do like, if you can have, say, 200 qubits on one, then you can flip another one on it to have 200 qubits, but they are then going to be connected in different ways. That's an engineering thing to like figure out. Some people are also trying to see if by connecting different fridges, so if this fridge can hold maximum of say 1,000 qubits, then if we can have a system or a quantum processor with 1,000 qubits here, you have another one here, and you connect everything together. So even though that's still not that's still not cost friendly, we still don't really know, at least for superconducting qubits, we still don't really know how people are going to get 1,000,000 qubits. So that's still like a research thing that people are still trying to figure out. So yes, that's a very good question, and And yeah, so whatever you have to do for your system or the number of qubits you have, you are restricted by the spacing that you have in your chip. So whatever the size of your chip is determines the number of qubits that you have. So maybe someone later can come up with a nice way or a nicer way to get things of squeezing qubits, more qubits into your system so that you can have more qubits on your chip. But for now, you are still one is restricted by the size, the size of the dilution refrigerator or the size of the wafer.
Okay, thank you. I have 4 questions in all.
Okay.
The second question, which might be, well, to me, maybe from your own end, it might be trivial, but to me, it's not as trivial as you might assume it. I want you to talk about the relationship between the qubit, its frequency, measurement, then the resultant heat, like you mentioned now, that makes it result into whether a ground state, exact state. Then, with relationship to the gate, you described that an X gate can be that expression V T that is expressed as sine of omega A, sine of omega stuff, and whatever. Why I want to say that, how do you relate these together and then talk about the kind of heat generated in the end product? Because we are using those terms and they seem to connect. Yeah.
Yes. Thank you for the question once again. And so let me see if I can go back to this. So a qubit, let's say we have a qubit, which is when we connect a capacitor with Josephson junction. So the frequency of the qubit, what we really mean is the um the 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 transition frequency from that takes you from 0 to 1. So in theory, what we really know is like we have qubit is in state 0 and qubit is in state 1. But in superconducting qubits, how you move from state 0 to state 1 depends on specific energy source that you insert or you send to your qubit. And that's so for microwave pulses, that is so for any microwave pulse in general, they are always written like this. So it's like you just send let's say this is a microwave generator. Give me a signal with a particular strength and a particular frequency. So now, after you try to, what we mean by the qubit frequency is like if our qubit is at ground state, if I send in a microwave pulse with energy h bar omega 01, then that qubit, it will excite the qubit from 0 to 1. So when we say the frequency of the qubit, it's usually the transition frequency from 0 to 1. And that's what it's been. Let me see. That's what it is being done here. So this measurement is saying I have a signal. I'm setting a signal into the fridge. The signal is I'm going to vary the frequency of the signal. So that's why you have from 4.2 to 4.7 gigahertz. Then I'm going to measure the response. So if I send in a signal of 4.2 gigahertz and it's not the transition frequency of the qubits that I've made, you are not going to get anything. Then I can sweep across this frequency range. So the moment I send in a signal that is of the frequency, the transition frequency of the qubit, which transition frequency of the qubit's energy level from 0 to 1, then I'm going to get a response that tells me that this is doing something. So it's a bit more complicated than this, but when one is familiar with, so if I see a measurement like that, I can easily tell that this is a qubit. But the idea is you send in pulses at different frequencies. So you send in at 4.2, you send in at 4.7. So it's not as discrete as this. You send in 4.21, 4.22, you go from that to 4.7. Sometimes this can, if you move really slowly, this can take 30 minutes, and sometimes it can take 5 minutes, depending on your knowledge of what your system is. So the idea is that when you send in at this particular frequency, then you excite the qubit. So now you know, so now one knows an idea of what the frequency is going to be. Then what we want to do is, like, now that I've kind of narrowed down what the transition frequency of the qubit is, then my gate is something that changes, that when I apply it, it takes the qubit from 0 to 1. So now that I know something, that I know that if I send in a signal of frequency omega d, like let's say of omega q, the qubit frequency, something happens to it, but I don't know if it excites it to the energy, the one state. So for example, if I send in a signal where t is 0.04, it takes it here, but this is not the maximum for the two computational subspace. The maximum level is 1. So this doesn't take it to 1. So that's what we want to calibrate here. So after we figure out what the frequency is, now we want to vary what the timing is. So to vary what the timing is, you do the same thing from 0 to some energy, for some time. This is for 14 microseconds. So you apply at t equals 0, you get your response. T equals 0.2, you get your response. So when you get something like this, you can see that it's like you are rotating from a block sphere. You are rotating from 0 to half to 1, back to half to 0. So you are getting from 0 to a mixed state of 0 and 1 to 1 back to, so this is like a rotation about a block sphere about the x-axis. So then when you get this, then you can fit in to your data and figure out what the time for the maximum point is. So the timing here will get you what this is, what the t is. So everything together, for the amplitude or the power, the frequency, and the time, this is what gives you your X gate. So we can also do the same thing for Y. We can also do the same thing for Z, or any quantum operation that you want to perform. So what we do is, we know that if I apply X to 0 for the ground state, it takes me to 1. So what pulse am I going to, what specific pulse am I going to apply that gives me that thing? So this is so that's how you calibrate your gate. So for the qubit, you the transition frequency, when we say the qubit frequency, which is the transition frequency from 0 to 1, when you cool down, like here, when you cool down to the lowest to the at least it's about 15 millikelvin that we can get to, but we know from theory that if we cool down to this kind of temperature, you don't have at that kind of temperature, you don't have any energy source that can excite your qubit. If your qubit is about 5 gigahertz, if it's about 4 gigahertz, you calculate what it's going to be. If it's about 6, you calculate what it's going to be. But everything should not be. It's not going to. So this is way, the common base temperature is like 15 millikelvin. It's way lower than 0.24 Kelvin. So when you cool down to this, we also measure, there is like a screen that tells you what the temperature is in the base plate. So when you know that you are at this temperature, then you know that your qubit is at the ground state. Even at that, like I said, this is a measurement of the ground state. Even at that, I can see mostly my qubit in the ground state when I take 5,000 points, 5,000 shots. But at some point, some things happen, and that is sometimes how you calibrate. For example, here, you take this data and you can do some machine learning algorithm to calculate what the fidelity of your what the fidelity of this is. That is, if I have 50,000 points, I have 2 different blobs. So what's the fidelity that is, if I apply this, what's the probability that I'm going to end here? You just like you can do the calculations and you see that's why how they quote the gate fidelity from, like, you can get some numbers from IBM website. The gate fidelity is this percent. The gate fidelity is this. So things like this are how you calibrate everything. I don't know if I've answered all the questions, but if there is any that I've not answered, please.
Yes, I think I get it clearer from your explanation. Thank you so much. So the last, it should be the third question, but I can combine with the last one.
Okay.
They could also be answered together. Yeah. The first is, I don't know why IBM says they will use superconducting qubits. I don't know. Maybe there's a reason for that, and you can answer since you're exposed to that. The
Yeah.
second one is for an upcoming should I say researcher or quantum enthusiast. What is your advice in the area of study that one can research into, particularly considering our background here, that the exposure is still very, very limited?
Yeah.
Thank you.
So on the first question, I think the reason why so I guess many people will have different reasons. They will say maybe they are going into the field, but one of the key reasons why, say, IBM and Google are going into the superconducting qubit field is because the fabrication parts. Because this is, if this doesn't really go well for us, like if we can't get 1,000,000 qubits or some 100,000 qubits that we want, then we are not going to do anything. But the fabrication part is based on the current semiconductor fabrication, which is how you fabricate the chip for your laptop, for your phones. So the whole thing is like it's based on that. So we know how to pattern tiny things, tiny qubits. So everything here is really borrowed from, like, what we do here is almost like it maps to exactly what how, like, the different type of semiconductors, silicon semiconductors are patterned on the chip that powers our what is it called, our current classical computers. So some people would say maybe the coherence times, but this the superconducting qubit doesn't give you the best coherence time. But the scaling part is like if we can figure out a way to fit in 1,000,000 qubits on a particular chip, we know from measurements there are industries that already they have already done most of the work for the measurement, for the fabrication, for everything. For example, this simulation software, it's what they also use in semiconductor industry. The design AutoCAD is what they use. The packaging is the same thing. Like fabrication is the same. It's the same, or the same fabrication room. So I think, to me, that's one of the main things. And like the theory, the um the experimental part is like it's something that is already known. And since we figured out how to like get a qubit out of like a solid state system, then that's one of the reasons why they are going into. I think from their website they will have some other reasons that they have, but I think the main thing is we know how to do some of these things from the current classical computer industry. So then, moving from that to patterning our qubits, it's still a solid state system. Patterning our qubits, engineering everything else, it's not as hard as like saying I think Microsoft, that they are building their whole system from scratch. So yeah, that's one of the main reasons I can say for IBM and Google, and for other for some other groups. Like in general, it's simpler to build on something that's already been known. And for how to get into the field, like, unfortunately, unless one is in the lab that does things like this, there is really little you can do. So the best thing one can still do is the theoretical and the maybe theoretical simulations. because like if one doesn't have a qubit, or you don't have like the resources to do things like this, these things are expensive. Like there really little one can do, but the best, like almost everybody will all get started with the theoretical part, learn the algorithm, learn the courses, and if one is interested in like pursuing, say, the experimental part, then one has to go somewhere that is not in Nigeria. Unfortunately, we don't have, to the best of my knowledge, we don't have any labs that have like experimental fabrication or superconducting qubits or something else in Nigeria. So yeah, I think there are some opportunities outside of the country that one can exploit or get into. But the best, I think, to the best of my knowledge, the best one can do is the theoretical aspects. It's just to, for example, you can for Qiskit, you can learn the quantum algorithms, you can learn the quantum circuits, and if you want to you want to run your results or whatever you have on a real system, there is also a way to also do that, even though it's limited. But yeah, that's I think for now, unless things change in Nigeria tomorrow and they want to fund quantum information science, then maybe we'll have a system of our own in the country. But yeah, I think it's still the correct theoretical and simulation part that one can do. Thank you for the questions, Masani.
Okay, thank you so much. I quite appreciate the great exposure from your talk, from your answers. I know that when we did this last year, we decided we were going to try to create a device. I mean, by formulating a quantum computer. Mr.
Yeah.
Mr. Tiabi was one of our leaders. I think now
Mhm.
we know the task involved. We appreciate you so much. We hope you give us some of these materials. Particularly, you refer to some references in the
Yes, I
beginning,
can.
then this
Yes.
particular presentation slide, and maybe we'll keep
Yes.
communicating for subsequent collaborations
Yeah.
since we had you as one of us here. Thank you so
Yeah.
much.
Yeah. Thank you for having me. Thank you.
All right, I do have one question. I was
Okay.
wondering if it's possible for anyone who is interested here to contact you, whether you would maybe send a means for us to be able to contact you with.
Yes, I think Victor has my contact, and and yes, I'm also on LinkedIn, and I'm also active with the Q Nigeria group. So so from Victor, I think Victor can contact as my contact, and we can move on from that.
All right, thank you so much.
Okay, thank you.
All right, thank you for being here. All right, on that note, we'll be closing this session. We'll be back by 1 p.m. sharp for the last speaker of today, Mr. Isaiah. So please stay tuned for the until we have until 1 p.m. Thank you so much.
Hello, can you see my screen? Hello? Hello?
Hello, Mr. Isaiah.
Yeah, can you see my screen?
Yes, you can see your screen, but not what you're sharing. Please, could you give us maybe 3 more minutes? There's a technical difficulty here. I want to fix it a little bit so that you don't
Okay,
start.
no problem, no problem, no problem, no problem.
All right.
I made him close.
All right, Mr. Isaiah, we're ready for you. You can start now.
Okay, can you hear me?
Yes, we can hear you.
Okay. So, good afternoon, everyone. I am Isaiah Nuluapo Harem. So, I'm grateful for this opportunity given to me to actually give a talk in this year Qiskit Fest. So, I'm grateful to the organizers of this program. So, The topic of the talk this afternoon is what is titled Quantum Works for Beginners, Generating Music with Quantum Markup Processes. So let me do a kind of quick introduction about me. I am a member of this club, and I just finished my MSc at AIMS, South Africa, where I was able to work on generating music using Markov chains and processes. So this talk this afternoon is like an overview of what I did during my MSc. Now, if you go to the basic of this quantum. So let's check the classical and quantum differences. We know that the classical computers, you can only use is either 0 bit or 1, not the 2 at the same time. But in quantum says that we can actually combine these 2 bits simultaneously in such a way that the square of the sum of the squares of their amplitude will give us 1. This is what linear algebra says, that linear combination of the bit 0 and 1, which is not possible in classical system. So these are important superpowers. I call them superpowers. These are what quantum is using to outpower classical. The first one is superposition, which I just explained. The second one is interference of the amplitude. Will the amplitude interfere, or will it interfere constructively or destructively now? If it does constructively, that means it is added together. The other part, it means there is difference between them. And the last one here is entanglement. We tell us that two quantum systems can be measured simultaneously at the same time, in such a way that what you do to one will actually affect the other. The reason is because they are entangled. Even though they may not be physically present, but anything you do to one, what affects one may affect the other system, which is not possible also in classical system. Now, going to the work per se, the first thing that was done is classical random walks. This classical random walks has the background in graph theory, in mathematics. When we have a graph, which is a set of vertices and edges, and we should know that each graph is standing for a transition matrix, which transition matrix composes of different transition probabilities. Now, if you call P subscript U phi as the probability of moving from a particular node U to another node phi, now the evolution of the state is given as this. The reason why we have it like this is it is row stochastic process. Assuming it was to be column stochastic process, the transition matrix will come before the stationary distribution. Now, let's dive into music. The beauty of this project is I combined 3 things together: music theory, physics, and that is quantum part, and also mathematics, even computer science. They are combined together for this project. And my end goal of this project, has not been reached yet. Has not been reached yet. You will see at the end of this talk, the end goal is to use real quantum computer in order to see how music can be generated, not using quantum processes alone. Now, let's say we have a fetus now, which is a tuple. Tuple means that you combine things together. Note, let me show the diagram very well for us to see. We have note. There's no music without note, actually. Notes, when we are saying note, in music, we have 7 different letters that we use to represent note, A to G, A to G. So it now depends on which of them are we singing on now. But literally, let me pick C now. Let's say I'm working with C to be C, E, C, D, E, F, G, A, B, 7. That means C there is standing for do. D, which is the second letter that follows D, C rather, is standing for re. That's how we have do, re, mi, fa, sol, la, ti, do. So no music we can't have music without this note. Another thing is duration. Duration means the time for each note to sound. Another thing which was considered is intensity. Intensity means how loud or short the note should sound. Should I want it to be moderate? Should I want it to be very loud? Should I want it to be loud? So I combined these 3 things together to represent the note of each of this musical graph. You can see it. You can see it better. Let me enlarge this for us to see. I hope you can see it clearer now. Each note is standing, is representing the tuple of notes, duration, and intensity. And if you look at the edges, here we have different weight there. They are telling us the probability. This is a weighted musical graph in such a way that each edges is weighted. And we shouldn't forget that when we are working with row stochastic matrix, it means that the summation of the row matrix will be 1. So if you pick a node now, the sum of the outgoing edges must definitely give us 1. Definitely give us 1. Now, let me check a particular example of what I'm trying to tell us. We shouldn't forget that we are checking the classical random walk, because we can't just move into the quantum aspect without knowing the classical understanding of what random walk in music simply means. Let's say I pick a vertex to be a chord, CEG. This is what we mean by a chord. If you have any music enthusiast, we understand that this is a chord. C here represents do. This E represents mi. This G represents so. We call it do mi so. It's a chord. We use it to back up a song. Now let's say I want to now move. This is an example of what I meant by transition matrix in the other slide. Let's say I want to move from this C now to another C. If I call that probability to be transition probability to be 0.6. Now another one, if I want to move from C to E, let's say that probability is 0.2, and so on and so forth. If it's C and check the row summation of this matrix, we see that they all give 1, 1. This tells us row stochastic process. The example, the probability of moving from C to E now is 0.2. Yeah, that's what I'm trying to let us know. Because the knowledge of this is very important when we are talking about Markov chain or Markov process. Because random walk is a typical example of this Markov chain that we are talking about. This is the evolution. The evolution says that the initial vector, the initial state vector that you pick, let's say at time t equals 0 now, this is my initial row vector. And I want to get the evolution of the next state that I will be musically. So it will just be the multiplication of this row vector with the transition with the transition matrix that I have from the musical graph. So this will actually give me the state evolution of the next state at t plus 1. So this is just what it's telling us. So this is just like different examples of state evolution. So at t equals to 1, let's say we have this. So if you multiply it with the transition matrix that we have from the musical graph, so that will generate the next stationary distribution of the journey. So if this process now continues, let's say it continues, we do it, we continue, t equals 0, 1, 2, and so on and so forth. There will be a particular time that what's it called? This thing will converge. This vector will later converge back to our starting point. That's why we call it stationary distribution. So this is like the important theory of Markov chain. Now let's now go into the quantum part of what we are seeing, quantum works. So quantum work is leveraging on what's it called now? The unitary operation. The unitary operation in such a way that if I have my initial state to be this size 0, ket of size 0, so the matrix now will not be like that of the classical. The unitary this unitary operator will now be what will give me the evolution to the next state. And this we have this because of the superpowers that I explained earlier that quantum has over classical. So another interesting part, another interesting important fact about quantum is that there is a particular quantum quadratic speed up that quantum gives us. If we look at this now, this is telling us the time of the number of steps in order for us to have a particular iteration done, to get a particular task done. Let me use that simple word. So classically, it is giving us 1 over the spectral gap, but the quantum is giving us a particular speed up, quadratic one, which makes things and iteration faster than classical counterparts. Now, the first quantum work we want to talk about is the coined quantum work. The coined quantum work. Now, The core idea under coin quantum work is just two. That is, we are going to have a worker which will use the vertex of the musical graph as its position. And also, he will use a particular coin to make his decision that, oh, where should I go? Okay, I'm on this vertex, on this graph now. Where should I go to? I can't, this quantum worker cannot just move randomly like that of classical. So there's a particular advantage here. And that advantage is coin. That coin, the decision of the coin, will now determine what to be done and the direction to go. Oh, if I have K0 now for this work now, I chose my K0 if the result after the coin has been applied is 0. It shows that the quantum worker will move to the left. And if the result is now Ket1, it means that the quantum worker will need to choose right direction, not like the classical counterpart that I showed you. Now, this is the Hilbert space composition. That is, it is the tensor product of the position and the coin operator. So, and coin operators, we have different types of coin operators. We have all our poly gates, X, Y, Z. We have what's going on now? I. We have adamant and the like. So these are what comprise of our operators, coin operators rather. Then, apart from that, when you get the result, there's another operator that is important. That one is named shift operator. Shift operator is the one that we leverage on the direction gotten from the result of the coin operator. This is the summary of what I'm saying. This diagram is the summary of what I'm saying. If I have my initial state now, and I apply a coin operator, then the result now will now be leveraged on by shift operator. The shift operator will now take me to the next state rather. So you can see that there's a particular evolution from my initial state to state +1 now, T+1. This is what coin quantum work is all about. So let's say I have adamant now. Let me use adamant as my coin, as my coin here. Now the evolution, this is the composition of the evolution, unitary matrix there. It gives us that we have the tensor product of the I identity and the coin. You shouldn't forget the coin. The coin here will be adamant. This adamant represented by this matrix. So the shift operator we should look at it. Now this phi is representing fetis phi. Now this D is the result gotten from our operation. What's going on now? The operation when C was applied, when the coin was applied. So if the decision is now telling us that K0, so the shift will now be applied to this state in order, based on my initial condition. Oh, if I have K0 now and the vertex is 1, that means, okay, let me look at this diagram. Let's look at this diagram together. Let's say I'm on this vertex 0 and I apply my coin, and let's say the result is now 1, for example. That 1 is telling me move to the right. So I will no longer move towards the left. I know that if I move to the left, I'm moving to the vertex 1. So automatically, my decision will take me to vertex 2 of this graph. So let's check this example out. Let's check the example. This will give us a clearer picture of what I'm explaining. Now, the first thing here is I have my initial state. And let's assume now that the worker is on factor 0. He wants to make decision on where to go. Am I going to factor 1 or am I going to factor 2? Now, before any decision could be made, the coin operator is applied. And this thing is telling us, Adamant, I said it earlier that we have different coins that we can use depending on our choice. Here, Adamant is used as coin operator here. Then after this process, the step 1, let's see what happened. Adamant collapses coin to left, meaning that it collapses the whole process into Ket 0. Ket 0 pertaining this project is taken to represent left, while Ket 1 is representing right. Now, shift operator moves worker to factors 1 according to initial condition I put. So my left is 1. My right will take me from 0 to 2. Since the result is left, so the worker is no more on factor 0 again, but now on factor 1. Now, meaning that I'm no longer on the state 0 again. I'm now on state 1, which gives us this tensor product between 1 and the result of my coin operator. Now, if you want to move forward or further, so this is the step 2, meaning that apart from that, the whole process will still be repeated in order to move from that state and to continue and so forth, and so on and so forth. Now, apart from that, I did some simulations in order to see how probabilities vary, how they vary using different coins. Now, the first one is Adamant. I picked a particular musical graph. Now, I showed you one of the graphs because I have different musical graphs that I worked with during the project. So one of them is what I showed you in the early part of this slide. Now, during the simulation, I wanted to see how the evolution of the worker, the probability of the worker, how it varies over time and over from one vertex to another. The graph I used here to do this evolution happens to be 536 musical graph. That is a musical graph which has 5 nodes, 0 to 4. That's why we're having, let me try to bold one so that we see it better. Meaning that at step 0, I chose my initial, what's it called now? The initial vertex point to be 2. That's why it is starting on 2. At step 0, there is 100% probability. That's why we have step 0 to have this. So at step 1, there is something here. Something happens here. We can see that the worker has moved from factors 2 into 2 different vertex, 1 and 3. But the probability is equal. This tells us the power of this guy, H, Adamant gate, in order to create superposition. equal chances of that worker to be in multiple states at a particular time. So these are the results of what happened in the simulation over different steps. This is telling us step 2. This is what happened. This is telling us step 4. If we add this, the probabilities of each, what's going on, of the state of the worker, this quantum worker, it must definitely give us 1. So this actually gives us like the pictorial understanding of how adamant gate can be used as a coin operator. Now, another thing that was considered is identity coin. Identity coin. Identity coin. So here now, let me bold this also for us to see. So 2 also, vertex 2 was chosen as my initial state of the quantum worker. So, but what happens here is it moves from 2 to 1 to 0. I chose left to be the to be the initial direction. That's why the evolution is going towards the left. That's why the evolution is going towards the left. 2, 1, 0. Because we shouldn't forget that I said this earlier that I used 5 vertices musical graph from 0 to 4. This is step 1 on vertex 1, step 2 on vertex 0. You can see now. Step 3 on vertex 4. Another interesting thing is that it's just going 2, 1, 0, 4, 2, 1, 3, 3. You can see it's now on 3, now on step 4. 3, 2, like that. 2, 1, 2, 1, 0, 4, 3, exactly like that. So that's just telling us about how identity, what's going on, as identity coin behaved when used as a coin, when used as a coin. Another thing is this poly X coin. That one flips the bit. Let's see. Let me make it so. You should not forget that I said I chose left as my initial direction. So, but look at this now. It flips the direction. It flips the direction from 2 to 3. Instead of that 2 to go to 1, like the way we saw it for identity now, but it actually did otherwise. 2, 3, 4, and like that. But the problem here is the initial vertex, the initial state of the quantum worker is 2. We move 2, 3, 2, 3. That's how X. I could notice that X gate was behaving, moving from 2 to 3, 3, 2, 2, 3, 3, 2, 2, 3, 3, 2. So automatically, if I use this coin, I mean X, as my coin in order to generate the music, automatically it will be giving me repeated pattern like 2, 3, 3, 2, 2, 3, 3, 2. That's the penalty. That's the implication now. 2, 3, 3, 2. You can see that's how it is doing. You can see 2, 3, 3, 2. It will not give me a kind of harmonic harmonic melody that I actually look for, that I actually wanted. So that was the reason I did not even bother to use X at all. I did not use X in order to generate any music because I know that it will not give me a, like, I don't want music that will be 2, 3, that will be sounding like that. That will be in that pattern, 2, 3. The pattern I was with, we still go back again. No, that's not an interesting part of the music, because the music is the is the foundation of, is the interesting part why I'm doing all this mathematics actually. The same thing happens to Y, but just that there is phase flip joined with beat flip for Y. Z coin now. Z coin. This also wants to resemble that of I, but not totally. 2, 1, 0, 4, 3. But the difference is the, how will I put it now? The difference in the beat, because I is just telling us that just be going to the left, just be going to the left, just be going to the left. There's a particular time that the whole process was mixed up actually for said. It did not later give me constant thing like I, the identity, I mean. Now, to the other part of the quantum work, the first part, I'm done with the first part now, coined operator, using coined different coins in order to determine the direction of the quantum worker. Now, this is another concept. This concept was given by Segedi in his paper. So when I read the paper, I noticed that Segedi quantum work has a potential of giving me dynamic music. So if I use the quantum work to help my quantum worker in order to move along the vertices of the musical graph, so it will give me better music. So this Segedi quantum work actually leverage on the random, the classical Markov chain that we know. But the initial thing he did was that the first thing to do is to start from the classical, then turn the whole process quantumly. You will see it. It's a very interesting theory. So here we don't need coin. You don't need coin to tell us the direction that we need to go. Here now, Segedi made use of bipartite graph. So in that paper, so he said when I have irregular graph, so I can make a bipartite double cover from that graph. You will see it later. This is it now. This is the whole mathematical description of what Segedi is all about. So it tell us he made us know that, let's say you have your musical graph to look like this now, regular graph. So the first thing to do here is to create a bipartite graph from there. And then how will I do that? I actually give like an explicit explanation of this diagram later, but I will only explain this mathematical stuff now before I continue. Now, it says that you need to find the probability. Then I will explain what X and Y is later on. This light blue note is representing X. This green note is representing Y. This bipartite graph is the same as the irregular graph we have. Figure 2 here is telling us irregular graph. Figure 3 here is telling us bipartite graph. This bipartite graph was taken from the regular graph. And how? Let's check. We have 6 nodes here, 1 to 6. 1 to 6. Let me pick this node 1, for example. Now, let me pick this node 1. We can see that this node 1 is connected to node 3, node 2, node 6, and node 5. Meaning that there is 1/4 probability. I'm talking classically now. I'm not yet, because Segedi is trying to tell us that we can move from classical directly into quantum aspect. We don't need any coin. Now, it means that since I have 4 edges around this node 1, it means that if a worker is on this node 1, that worker has 1/4 probabilities of moving to any of its neighbor. That's just meaning. Let's see that one. That one, I'm now explaining figure 3 now. That one, I'm on light blue now. 1 under light blue. That one is connected to 6, is connected to 5, is connected to 3, and is connected to 2. Meaning that I constructed this bipartite graph from this irregular graph. That's just the idea behind that. That's the first thing to do. Telling us that I can create X and Y from state X and state Y, rather, from this irregular graph. That's the starting point. Then, after getting the probability, I will need a projector, which is telling us I will need projector A for X, I will need projector B for Y. Projector A is telling us the summation of the outer product of that X, and the projector B is telling us the summation of the outer product of Y. Let me repeat myself. This node represented by this color, light blue, is standing for X. The green part is representing Y. So after that, I will need reflections. Reflection for RA now is giving us 2A minus identity of the Hilbert space. You shouldn't forget that that will be unitary, identity of the Hilbert space. And the same thing is applicable to B now. I will need reflection for the B counterpart, which is representing Y, nodes under Y. Then I will now find my work evolution. This will now give me the state now. That is the multiplication of the reflections for RA and RB. You will see the explicit example later. This diagram is telling us how Segedi work is constructed from the classical matrix which we are all used to. Then we construct quantum states for X, for Y. We should not forget that these nodes X and Y are gotten from a graph. I used simple graph for us to see it clearer, but for the project, I used a musical graph, which was a bit complex. Now, here now, we later find the projector A, then projector B, then we find reflection, then we find the work operator represented by W. This will now give me my evolution now. This is how the whole thing will be evolved. When I have my work operator to be this, so if I apply it on my initial state, automatically that will give me the next state that my worker will actually be. This is the explicit example of the diagram shown earlier. Now, in the diagram, we have 6 nodes diagram, 1 to 6. So from the bipartite double cover graph that I drew, so we have our node. I said the first part of the node is representing X, while the second part is representing Y, meaning that X is a set of X1 to X6, Y is a set of Y1 to Y6, like that. This is classical. Now, the example I gave earlier, we have 1/4, 1/4, 1/4, 1/4. Exactly. Here is we have it here now. For state 1 now, for state 1, it means if we go and check the diagram again, probability of moving from X1 to Y2 is 1/4, X1 to Y3, 1/4, 1/4, 1/4. The summation will give me 1. The same thing, if you check state 2 now, X2, that means for X2, there are 3, for node 2, there are 3 edges. Sorry, there are 3 vertices connected to node 2. 3 nodes connected to node 2. That's why we have 1/3. This is telling us classical probability stuff. The same way for X3, the same way for X4. We can see that X4 only has a node connected to it. That means it's just node 3 that's connected to node 4. That's why X4 is going to Y3, and that is 100% probability, meaning that a node is connected to it. No other node is connected. The same way, the other part, 6th node is connected to 2 nodes. It only has 2 neighbors, node 1 and node 2. So having the probability to be 50-50. Now, after doing that, you do that of the classical probability for Y also. And that is gotten here, is explained here better. Yeah. After that, we now move into quantum part. Now, the quantum part is represented by this now. For ket X, this is telling us the state. This will later give us the state formation of what is going on in that X. And what the other one, the other part now, psi Y, is telling us what is going on, the state of what is going on for Y. So I also did it explicitly so that for us to see it better. The same way, but different approach. This is different because we have the amplitude now already in quantum state. And we should not forget that we cannot just add the amplitude, unlike that of classical. So here now that it shows that we have four different probabilities there. That's the place cannot contain. That's why I put plus dot dot dot. So I have 4, and this 1/2 is telling us the amplitude for each state. 1/2, 1/2, 1/2. You know that for quantum, I gave the formula earlier that from Bond's rule, you know that the summation of the square of the amplitude will give us 1. So this is where we can actually apply that. Since we have 1/2, 1/2, 1/2 square, 1/2 plus 1/2 square, we actually get 1 as our answer. So here now we have moved. We have moved from the classical, let me call it state now, to quantum state for X and Y. For X and Y. The reason why I didn't for this psi Y4, the reason why I didn't have any amplitude. The amplitude here is 1, meaning that is 100% 100% probability. Yeah, you can see that second is very interesting. It's very interesting. You don't need coin in order to have our probability of transitioning from one state to another. The other one now, we can see that this is 1/√2 for two different states, meaning that that's 50% chances, equal chances of moving from this state. Now, the same thing that I did to the coined simulation, is I still did the same thing to Segedi, whereby I simulated it in order to see the pictorial evolution of the probabilities over 5 musical graphs that I used. The same graph that I used for the coin quantum work is what I used for this also, in order to see how the probability changes over time for each node of the musical graphs. We have at the initial step, rather, we have everything being equal, everything being equal, everything being equal. At step 1, you can see that the probability now varies now. Probability now varies. At step 2, you can see these two guys have the higher probability compared to the 3, and so on and so forth. So this tells us this tells us the difference between the coined quantum work and the Segedi quantum work. It's also Segedi also brings about quadratic speed up in eating times. When you are talking eating times is the number of steps required to move from one node to another. So it actually this particular it speeds that step up, unlike the classical, because during the experiment, I made sure I did experiment on classical in order to generate music classically before I ventured into quantum, because I needed to know if I do this classically, what will be my result. So if I do this quantumly, what will be my result? And I don't want to only use one way, because even though I use one way for classical, because classical is still classical, but quantum, that was the reason I used 2 different ways, point and Segedi. Let me now see the output of these guys. Now, I put them together now in order for us to see the differences between them. The upper part, the diagram above, the picture above is telling us the evolution of the Adamant gate over the musical graph rather, and the picture, the image below is telling us the probability evolution for Segedi quantum work. We can see for step 0, you just have 100%. For this now, for step 0 under Segedi, you have equal chances. For step 1, it's now 50-50. For I use Adamant to represent the coin, to represent my coin quantum work here. So 50-50. Here now, the probability is not 50-50, it actually varies. This actually is the summary of the simulation for the different quantum works that were used in the project. Now, at the end of the day, I now brought the musical creativity now, because the project, I said it earlier that this project comprises of different aspects. Music theory is, because there's no any music without any music theory. So I brought the creativity of this musical knowledge in such a way that let me now have 4 different musicians. Let me have 4 different musicians that will be playing at the same time. I know this thing this thing is not possible in real life, actually. This thing is not possible in real life. Has not been possible yet, because in real life, I'm a musician, I'm a keyboardist. How is it possible for you to play to 4 different musicians playing together at the same time? How is it possible? Automatically, it's very difficult, because the way this composition that was done, this picture, this musical graphs is telling us 4 different musicians singing, walking. As they walk along the vertices of this musical graph, they were generating music. They were singing at the same time, and it was possible. The reason why it was possible is because of quantum evolution. That's the advantage. So, but in physics, in real life, I was wondering that, can this thing be possible? Because one singer, you'll be thinking of somebody that knows music, you'll be thinking of how to modulate when the key changes, or how to follow the progression and the likes. Every musician, every instrumentalist, we used to follow the musician when singing. So you are now following 4 different musicians at the same time. Each one of them is playing is playing on different keys. The first one is playing on F mode. The other one is playing on G mode. Let me increase the size for us to see it better. I was able to see that it is possible with the help of quantum Markov processes for even many musicians to play together. It is possible, and the music will still be nice, actually. So we have F. This first musician is playing on F mode. The other one is playing on G mode. The other one is playing. This one is playing on A mode. This one is playing on C mode. Using the concept that I gave earlier, that each quartet is representing tuple of note, duration, and intensity, in such a way that, so the decision here I did, okay, this is what I did. I made sure that I used the concept of point quantum work for this, and also I used the concept of Szegedi for this, and now compared their sound. I have the product on GitHub, and at the end of this talk, the link is already in this slide for anybody who wishes to listen to it. Actually, even though I said something that my end goal is to use free quantum computer in order to do this thing, but as this moment, because of the time limitation for this project, so I only used classical computer. I used Python, classical computer, to do this thing. And I know that if with the new innovation and invention of the classical of quantum computing now, by the time I will continue this for my PhD, because this is what I look forward in continuing on. So I will be able to have like the resources in order to do this on real quantum computer rather. So this concept of music that was used here is what is referred to as polytonality. Polytonality means that we have different tones, but melodic tones standing together, playing together. These 4 musicians, they were playing using different instruments. One is using clarinet, one is using horn, one is using flute, one is using I only use brass instruments. I use piano for one, I use clarinet for one, I use flute for one. I've forgotten the 4th one now. But I make sure that they use related instruments, but not the same instrument, related instrument, in order to, and the composition are generated together. What A is doing, what B is doing, what C is doing, what D is doing. What I mean by ABCD is what these different musicians, these 4 musicians are combined together. All the sequences are combined together in order to form the combined music. So you can actually scan this QR code. You can scan it in order to, it will take you to the GitHub account where you can see the music that was created and generated. So to conclude my talk this afternoon, as at this moment, for this talk, we have actually seen the mathematical foundation for quantum creativity. Yes, given by Segedi and coined quantum world. So, and also there is a particular link to quantum algorithms. Yes. So I think I will stop now. So, provided there is question. Thank you for listening.
Thank you, Mr. Isaiah, for the wonderful talk. Do I know if we have any questions? Any questions from the audience here? Any questions from the audience online? Any questions? All right, so thank you, Mr. Isaiah. There are no questions on this end, and it seems there are no questions online as well. So I think with that, we'll be wrapping up the talk session from Mr. Isaiah. Thank you so much, sir.
Yes, so you are welcome.
All right, without further ado, we'll be going on to the last session for today, the question and answer session and review for the past week. So if anybody has anything to note or to say, or any questions concerning how the event is supposed to move forward, please do ask.
Sorry, I want clarifications on the last speaker. While he was saying that there's no possibility of maybe playing instrument at the same time, are you referring to a single entity playing different instruments at the same time, or different people playing at the same time in practice? Or you are trying to use that illustrations for the last simulations you did, and then the output you are bringing. So I want to find out, are you referring to single entity trying to play the instrument, or different people with musical skills?
Hello, can you hear me?
Yes.
Yeah, what I'm actually trying to say is, it is possible for us to have one musician now in such a way that different instrumentalists will be playing to this song. We have keyboardists, we have guitarists, we have lead guitarists, we have bassists, and we have drummers. Now, what I'm actually saying is, for us to now have a particular musician that will be doing the whole stuff, and everything will still be harmonic.
You mean a single musician?
Hello?
A different musical instrumentalists?
This is what I'm saying. The concept that was used there is a concept called polytonality. polytonality. Polytonality here is I use the musician in order to just explain it actually, because you know this was coded actually. The whole let me okay I'm actually stopped sharing the screen. So this was coded, but what I'm actually trying to say per se is that we have one more. Okay, okay. Let me start from the basics. Let's say, okay, what I did was I pick a particular key major, F major rather. From that F major, I now pick 4 different modes. Don't forget, it's still the same key, but different modes. And I say that let one player, for example, now one player, one musician, just use it together. Just know that they are the same thing. I mean them to be the same thing. To be playing on G. Don't forget, I don't know if you are music enthusiast now. We have on F now, F major. You have F G, A flat. Do you understand? C, D, E. Do you understand? So that's what. Okay, let me go back to this slide so that you understand what I'm saying. I'm coming. Can you see my slide?
Not yet.
Hello, can you see it? Can you see it? Can you see my slide?
Your slide is not yet visible.
What about now?
Just remaining small. I think it's showing us that
You see?
yeah, it's visible now.
Visible now. Okay. Now, what I'm trying to say here is that I pick a particular key for all of them, and that is F major. And in F major, we have F as the root note there, serving as do. Now, I did this logic in such a way that from there, so this F, this first musician will be playing on F mode completely. This G, this other musician will be forming its own from that F major, but its own root note will now be G. It will now be D, G, A, and so on and so forth. This, what's it called? The other third musician will be starting his own formula. You know, let me turn this over now. This is, I assume the other one is forming his own from Do. The first one Do. The other one is forming his own from Re. This one is forming his own from Mi. And this one is forming his own from So. You can see C, So. So exactly. This is the logic there. This is the logic here that I use. I don't know if you understand. Hello? Hello?
Hello?
Hello?
Hello?
Yes. I don't know
Yes.
if you understand what I'm saying.
Okay.
Hello?
Hello, I'm with you. Okay, you
Did
are
you
trying
get
to explain that if you are playing on key F, you are playing on key G, maybe single persons, that is not the possibility of making it harmonious together, playing on different keys would be difficult. Is that what you're saying?
yes, invariably, because same, but it's just what they are playing. It's just like one is playing, for example, now in this, let's say one is playing major, one is playing minor, one is playing pentatonic scale. You understand? But on
Yes.
the same key.
Okay. All right. Cleared.
Okay.
All right, do we have any more questions? Okay, in the absence of any questions, I think we'll call this a day. And then next week will be our hands-on lab session. So if you know anybody who's supposed to be here and hasn't been attending, please let them know that they would not want to miss out next week. So with that, I think I'll bid you all adieu and say good day to everyone. So see you all next week. Thank you. Okay, the time will be Thursdays 4 to 6 Nigerian time, Friday 4 to 6 Nigerian time, and Saturday 10 to 3 Nigerian time. The timetable will be sent to us, so anticipate. All right. Goodbye, everyone.